In the vast emptiness between star systems, a wanderer moves through space with the patience of geological time. Comet 3 Atlas carries within its nucleus the frozen breath of another sun, ice crystals that formed in a stellar nursery, perhaps dozens of light years from our own. Its trajectory follows mathematics older than planets, a hyperbolic path that speaks of interstellar exile, of gravitational rejection from some distant solar family. The comet bears no passport, no stellar allegiance, only the cold momentum inherited from its birth system's final gravitational goodbye. The visitor's nucleus stretches perhaps 20 kilometers across its longest axis, a modest mountain of ice and rock that has journeyed through the interstellar medium with the quiet persistence of deep space. Its surface temperature hovers near absolute zero, minus 250 degrees Celsius, cold enough that nitrogen freezes solid, that carbon dioxide becomes harder than granite. In this frozen state, the comet preserves within its bulk the pristine chemistry of its origin world. Molecules that have remained unchanged since they condensed from stellar winds in another part of the galaxy. The comet's surface bears no resemblance to the familiar dirty snowballs that orbit our sun in predictable ellipses. This visitor wears a coat of organic compounds darkened by cosmic radiation, molecules that have weathered the interstellar medium for millennia uncounted. Carbon chains and nitrogen ices create patterns across its rotating surface, like abstract art painted by particle bombardment. Methane frost forms delicate crystals in the shadowed valleys between ancient impact craters, while ammonia deposits create pale streaks across darker terrain composed of carbonaceous dust. Each rotation takes the comet through a 27-hour cycle, tumbling end over end with the irregular spin imparted by its last gravitational encounter in its birth system. This rotation creates no seasons, no variation in temperature across its surface, only the endless alternation of cosmic night and cosmic night. The comet spins through vacuum so perfect that human technology cannot replicate it, through space so empty that individual hydrogen atoms might travel for years before encountering their neighbours. Scientists puzzle over its precise composition, for spectroscopic analysis reveals chemical signatures both familiar and foreign. The isotope ratios whisper of stellar nucleosynthesis in a different neighbourhood of the galaxy, where heavier elements condensed under the influence of a star whose light has never touched Earth's atmosphere. The deuterium content suggests formation in a molecular cloud cooler than our own solar nebula, while trace amounts of rare Earth elements point to a supernova explosion that enriched the comet's birth region millions of years before our sun began to shine. Only the most sensitive instruments can detect these subtle variations, these fingerprints of alien chemistry written in spectral lines. The comet's interior remains largely mysterious, hidden beneath kilometers of radiation-darkened crust. Computer models suggest a differentiated structure, with water ice concentrated in the core and more volatile compounds like carbon monoxide forming an intermediate layer beneath the surface. Pockets of crystalline ice may preserve bubbles of interstellar gas, tiny samples of the galactic medium trapped during the comet's formation. These frozen time capsules contain isotope signatures that could reveal the chemical evolution of the galaxy itself, scientific treasures locked in perpetual winter. The irony settles quietly this ancient wanderer, forged in the furnace of another star, now approaches the gravitational embrace of our sun with the inevitability of orbital mechanics. It has travelled for perhaps millions of years to reach this moment, crossing the empty light years with the patience of cosmic drift. The universe operates on time scales that render human urgency meaningless, where million-year journeys unfold like planetary breathing. The comet's velocity relative to our solar system exceeds 40 kilometers per second, fast enough to circle Earth in less than an hour. Yet this speed represents the accumulated gravitational influence of countless stellar encounters across galactic time. As it moves through the outer reaches of our solar system, the comet experiences the first gentle tug of solar gravity, a force so subtle it would take sensitive instruments to detect the change. The sun's gravitational field extends far beyond the orbit of Pluto, creating invisible contours in space-time that guide the paths of all visitors. Yet this invisible hand begins to bend the visitor's path, drawing it inexorably toward the inner planets where Earth waits in its ancient orbit. Unaware of the mathematical certainty approaching through the darkness, the comet's hyperbolic trajectory carries it through regions of space that have remained undisturbed for billions of years, through the heliopause where solar wind meets interstellar medium, through the scattered disk where dwarf planets trace their lonely ellipses. Its path intersects no planetary orbits in these outer reaches, encounters no gravitational obstacles to deflect its course. The mathematics of celestial mechanics unfold with the precision of natural law, each moment of the comet's approach predetermined by the initial conditions of its interstellar journey. Radio telescopes track its progress with the patience of astronomical observation, measuring tiny shifts in its spectral signature as solar radiation begins to warm its surface for the first time in millions of years. The warming proceeds slowly, degree by degree, as the inverse square law governing stellar radiation gradually increases the energy flux striking the comet's dark surface. At this distance, still beyond the orbit of Neptune, the solar heating remains negligible, adding perhaps a few degrees to the surface temperature over the course of months. Yet already the comet begins its transformation from interstellar wanderer to solar system visitor, its chemistry awakening to the influence of our star's radiation. The first molecules of water vapour begin to sublime from its surface, so few that they would be undetectable without the most sensitive instruments. This marks the beginning of the comet's death, the slow dissolution that will accelerate as it approaches the inner solar system. Only took 4 billion years to cross the galaxy, and now it prepares to sacrifice itself to our sun's gravity in the span of a few brief months. The mathematics of gravitational influence operates with the quiet persistence of natural law. Invisible forces that reach across millions of kilometers to touch the interstellar visitor with fingers of curved space-time. Earth's gravity extends far beyond its atmosphere, creating subtle perturbations in the fabric of the solar system that will eventually guide the comet's fate. At this distance, still beyond the orbit of Mars, the gravitational acceleration amounts to mere millimeters per second squared, a force so gentle it would barely disturb a soap bubble, yet inexorable in its accumulation across the vast scales of orbital mechanics. The comet's path begins to curve, following the gravitational gradient like water flowing downhill through four-dimensional space-time. Einstein's equations describe this bending with mathematical elegance. Mass and energy warping the geometry of space itself, creating valleys and ridges through which all matter must travel. The comet experiences no sensation of force, no awareness of acceleration, only the natural motion of a free-falling object following the straightest possible path through curved space. General relativity renders the ancient concept of gravitational attraction obsolete, replacing it with the more subtle truth of geometric inevitability. Tidal forces begin their microscopic work of disruption, differential gravity that pulls more strongly on the comet's near side than its far side. The effect remains negligible at this distance, creating stress gradients measured in micropascals, forces weaker than a butterfly's wing loading. Yet these tidal stresses penetrate deep into the comet's interior, exploring existing fractures and weaknesses in its ancient ice matrix. The Roche limit lies far ahead, that critical distance where tidal forces overcome gravitational self-attraction, but already the seeds of eventual fragmentation begin their patient work. The comet's irregular shape complicates the tidal calculations, its elongated form creating complex stress patterns that vary with its tumbling rotation. Computer simulations model the internal strain distribution, mapping regions where tensile stress might exceed the cohesive strength of primordial ice. The comet's structure reflects its interstellar history, impact craters and radiation damage creating zones of weakness that billions of years of cosmic ray bombardment have etched into its matrix. These ancient scars now serve as potential failure points under the gentle but persistent influence of Earth's gravity. Scientists puzzle over the precise moment when structural failure might begin. for the transition from solid nucleus to rubble pile follows complex physics that remain incompletely understood. Laboratory experiments cannot replicate the conditions of interstellar ice age by cosmic radiation, subjected to temperature cycles measured in geological time. The comet's interior may harbour fractures that have propagated slowly across millions of years, stress concentrations that await only the trigger of increased tidal gradient to complete their ancient work of separation. The visitor's density remains uncertain, estimated from its gravitational influence on passing spacecraft and the subtle perturbations it creates in planetary orbits. Spectroscopic analysis suggests a porosity approaching 60%, indicating a loose aggregation of ice and rock held together by weak van der Waals forces and the modest self-gravity of its small mass. This internal structure resembles a cosmic snowdrift more than solid rock. Fluffy aggregations of primordial material that never experienced the compression and heating that forged the planets into dense spheres. As the comet approaches the realm of Earth's gravitational dominance, its hyperbolic trajectory begins to flatten, the excess velocity that marked its interstellar origin gradually surrendering to the binding influence of solar gravity. The orbital elements shift with mathematical precision, eccentricity decreasing as the sun's gravity well captures more of the visitor's kinetic energy, yet the hyperbolic nature of its orbit ensures that this gravitational embrace remains temporary. A brief encounter measured in months rather than the geological ages required for true orbital capture. The comet's rotation axis precesses slowly under the influence of tidal torque, a wobble so subtle it requires careful observation to detect. This precession changes the orientation of the comet's elongated form relative to the tidal gradient, modulating the internal stress patterns in complex ways that challenge computational models. The precession period stretches across several rotations, creating a slow modulation in the tidal stress that might trigger structural failure at unpredictable moments. Deep within the comet's core, ancient ice begins to experience stress for the first time in millions of years. The crystalline structure that formed in the cold of interstellar space now faces forces that probe its fundamental cohesion. Water ice at these temperatures behaves more like rock than the familiar substance of terrestrial experience, its strength measured in megapascals, its failure modes governed by the physics of brittle fracture. Yet cosmic ray damage has created point defects throughout the crystal lattice, vacancies and interstitials that reduce the theoretical strength and create preferred planes for crack propagation. The irony accumulates with astronomical patience gravity. The weakest of the fundamental forces begins to overcome electromagnetic bonds that have held the comet together across interstellar distances. The same force that guides galaxies in their cosmic dance now works to dismantle a visitor from another star, transforming solid nucleus into a loose confederation of fragments. The mathematics proceed with the inevitability of natural law, differential equations that describe the slow victory of tidal disruption over structural integrity. Radio observations detect the first hints of outgassing as solar heating reaches deeper into the comet's interior, subliming volatile compounds that have remained frozen since the visitor's formation. Water vapor emerges at a rate of a few kilograms per second, creating a tenuous atmosphere around the nucleus that interacts with the solar wind to form the beginning of an ion tail. This early coma remains invisible to optical telescopes, detectable only through its radio emissions and the subtle way it scatters sunlight in specific wavelengths. The comet's surface temperature rises degree by degree as solar flux increases with the inverse square of distance, infrared radiation penetrating the dark crust to warm the ice beneath. Thermal expansion creates additional stress as different materials expand at different rates. The coefficient of thermal expansion for water ice differing from that of rock and organic compounds. These thermal stresses add to the tidal forces, creating a complex pattern of internal strain that pushes the ancient structure toward its breaking point. Ground-based telescopes track the visitor's approach with the patience of astronomical observation, measuring precise positions against the background of distant stars. Astrometric measurements reveal tiny deviations from predicted orbital motion. Perturbations that suggest non-gravitational forces as outgassing creates a weak rocket effect. The comet's nucleus acts as a natural thruster, jets of subliming ice creating small but measurable changes in velocity that accumulate over time to alter its trajectory in unpredictable ways. The gravitational three-body problem emerges as the comet enters the Earth-Moon system's sphere of influence, its motion now governed by the complex interaction of terrestrial and lunar gravity. Computer simulations model thousands of possible outcomes, each depending sensitively on the precise timing and geometry of closest approach. The mathematics of chaos theory apply here. Small uncertainties in initial conditions leading to vastly different final states. The difference between harmless flyby and catastrophic impact determined by factors too subtle for perfect prediction. Only took 30 million years for this visitor to cross from the heliopause to Earth's gravitational embrace. And now the final approach unfolds over mere months. Cosmic time compressed into human scales as interstellar journey becomes local encounter. The asteroid belt spreads across the space between Mars and Jupiter, like a cosmic graveyard. Millions of rocky fragments that bear witness to the violent birth of the solar system 4.5 billion years ago. These ancient stones follow their elliptical paths with the regularity of clockwork, unchanged since the epoch of planetary formation. When Jupiter's gravity prevented them from accreting into a world of their own, now they float in the vacuum, silent observers to the passage of an interstellar visitor whose hyperbolic trajectory cuts through their orderly procession like a knife through still water. Ceres, the largest of these remnant planetesimals, maintains its solitary vigil at the belt's heart, a dwarf planet whose icy surface preserves the chemical signatures of the early solar system. Its weak gravity creates no meaningful perturbation in the comet's path, yet sensitive instruments detect the subtle gravitational interaction as the visitor passes within a few million kilometers of the ancient world. The encounter lasts only hours in terms of closest approach, but the gravitational influence extends across weeks as the two bodies dance their brief pas de deux through the mathematics of orbital mechanics. Smaller asteroids tumble through space with the irregular rotation imparted by countless impacts across geological time. Chunks of metal and stone, some no larger than city blocks, others stretching across hundreds of kilometers, each following its own precise ellipse around the Sun. The comet's passage creates microscopic perturbations in their orbits, gravitational nudges measured in millimeters per second that will accumulate over millions of years to alter their paths in ways too subtle for immediate detection. The butterfly effect operates on cosmic scales, where today's infinitesimal change becomes tomorrow's orbital revolution. The visitor's velocity relative to the asteroids exceeds 30 kilometers per second, fast enough that any direct collision would release energy equivalent to nuclear weapons. Yet space remains vast even here in the relatively crowded asteroid belt, where the average distance between objects spans millions of kilometers. The probability of impact approaches zero, calculated by astronomers as roughly 1 chance in 10 billion for any given passage. The universe operates with such generous emptiness that even this apparent obstacle course poses no meaningful threat to the comet's approach. Scientists puzzle over the precise gravitational effects as the comet passes through this field of ancient debris, for each asteroid contributes its own minute influence to the visitor's trajectory. The N-body problem becomes computationally intractable when extended to millions of perturbing masses, even those as small as asteroids. Supercomputers model the largest objects individually, while treating smaller fragments as statistical distributions, approximating the collective gravitational influence of countless rocky fragments through probabilistic methods that sacrifice perfect accuracy for computational feasibility. The comet's passage disturbs the delicate gravitational balance that has maintained the asteroid belt structure for billions of years. Kirkwood gaps, regions swept clear by orbital resonances with Jupiter, begin to experience subtle changes as the visitor's gravity slightly alters the orbital periods of nearby asteroids. These modifications occur on timescales measured in millennia, shifts so gradual that they would require generations of careful observation to detect. The asteroid belt remembers this passage in the change frequencies of its orbital dance, a gravitational echo that will persist long after the comet has departed the solar system. Vesta, the second largest asteroid, presents its battered southern hemisphere to the comet's approach. A massive impact basin that exposes the differentiated interior of this protoplanet. The ancient collision that created this crater occurred early in the solar system's history, when bombardment rates exceeded current levels by orders of magnitude. Now the exposed olivine and pyroxene catch sunlight at angles determined by Vesta's 7-hour rotation, creating subtle variations in reflected spectra that allow astronomers to map the asteroid's mineral composition from afar. The comet's coma, still tenuous at this distance from the Sun, begins to interact with the solar wind in ways that create detectable radio emissions. Charged particles accelerated by the solar magnetic field encounter, water vapour, and other molecules subliming from the visitor's surface, creating plasma instabilities that generate radio bursts across a range of frequencies. Ground-based radio telescopes detect these emissions as brief static bursts, electromagnetic signatures that reveal the comet's chemical composition through the characteristic frequencies at which different molecules absorb and emit radiation. Trojan asteroids, gravitationally locked in Jupiter's orbital path at the planet's L4 and L5 Lagrange points, maintain their stable configuration even as the comet passes nearby. These ancient captives represent some of the oldest unchanged objects in the solar system, primitive materials that have avoided both the heating of the inner solar system and the collisional evolution experienced by main belt asteroids. Their dark surfaces reflect only a few % of incident sunlight, compositions rich in organic compounds that may preserve the chemistry of the solar nebula from which the planets formed. The irony settles across astronomical scales. These asteroids, prevented from becoming a planet by Jupiter's gravitational interference, now witness the passage of material that formed around another star entirely. The failed world of the asteroid belt observes the approach of alien chemistry, isotope ratios that speak of nucleosynthesis in stellar cores that died before our sun ignited. The local meets the cosmic in a gravitational encounter that will alter both the visitor's trajectory and the subtle orbital mechanics of countless rocky fragments. As the comet crosses the belt's outer boundary, its surface temperature has risen enough to increase the rate of outgassing by several orders of magnitude. Water vapour now escapes at tons per hour rather than kilograms, creating a growing coma that spans thousands of kilometres around the nucleus. This tenuous atmosphere begins to develop structure as solar radiation pressure shapes the escaping gas into the first hints of a tail. Ionized molecules accelerated away from the Sun by the magnetic field carried in the solar wind. Asteroid mining prospects, a dream of future human civilization, would find rich targets among these ancient fragments, metals and rare earth elements concentrated by processes that operated when the solar system was young. Iron-nickel asteroids preserve the cores of shattered planetesimals, while carbonaceous chondrites contain organic compounds and water ice that could fuel interplanetary expansion. Yet these resources remain locked in orbits that require enormous energy expenditures to access, gravitational wells that jealously guard their metallic treasures. The comet's passage through the asteroid belt marks a transition from the outer solar system's ice and gas to the inner system's rock and metal. Behind lies the realm of frozen volatiles, where temperature differences measure in tens of degrees. Ahead waits the terrestrial planet zone, where solar heating creates the complex chemistry of rocky worlds, and where Earth awaits in its ancient orbit, unaware that material from another star now carries enough velocity to bridge the gap between worlds in a matter of months. Near-Earth asteroids, those that venture closer to the Sun than Mars, represent the most dynamically active population in the belt. Their orbits evolve rapidly by astronomical standards, lifetimes measured in millions rather than billions of years before they either impact a planet or get ejected from the system entirely. Some may be extinct comet nuclei, volatiles long since sublimed away by repeated passages near the Sun. Their dark surfaces now indistinguishable from primitive asteroids, except for subtle compositional differences detectable only through careful spectroscopy. the visitor continues its mathematical journey toward the inner planets, carrying within its nucleus the frozen chemistry of another stellar system, while surrounded by the slow-motion debris of our own world's formation. Only took Jupiter's gravity 4 billion years to prevent these fragments from becoming a proper planet, and now they drift in eternal orbit, witnesses to the passage of interstellar material that will soon test the gravitational stability of the Earth-Moon system. Jupiter dominates the outer solar system with the quiet authority of mass, its bulk containing more matter than all other planets combined. A gravitational sovereign whose influence reaches across hundreds of millions of kilometers to guide the orbits of countless smaller bodies. The gas giant's 400 Earth masses create curvatures in space-time so pronounced that they serve as the solar system's primary gravitational crossroads, determining which visitors from interstellar space become long-term captives and which continue their journey back to the cosmic void. Now this ancient arbiter prepares to render its verdict on the approaching comet, mathematical forces that will either accelerate the visitor toward Earth or deflect it safely away from the inner planets. The comet's hyperbolic trajectory carries it through Jupiter's sphere of gravitational influence, that invisible boundary where the gas giant's gravity becomes stronger than the Sun's distant pull. This region extends roughly 50 million kilometers from Jupiter's center, a volume of space larger than Mercury's entire orbit, within which the planet's gravity dominates all orbital motion. Computer simulations calculate the precise geometry of closest approach, accounting for Jupiter's orbital motion and the comet's interstellar velocity to determine the moment when gravitational destiny unfolds, according to the strict mathematics of celestial mechanics. Jupiter's 4 largest moons, Eos, Europa, Ganymede, and Callisto, orbit their primary with the precision of a cosmic clockwork, each locked in gravitational resonances that have persisted for billions of years. These Galilean satellites contribute their own minute perturbations to the comet's path. Tiny gravitational nudges that individually amount to nothing but collectively might alter the visitor's trajectory by fractions of degrees. In the sensitive mathematics of orbital mechanics, such small changes can determine the difference between collision and miss when scaled across the astronomical distances that separate planets. The gas giant's magnetosphere, largest structure in the solar system after the Sun itself, extends its invisible influence across regions that dwarf terrestrial scales. Charged particles trapped in Jupiter's magnetic field create radiation belts so intense they would prove lethal to unprotected human explorers. Energy densities that rival the interior of nuclear reactors. The comet's tenuous coma begins to interact with this magnetosphere as it approaches, charged molecules in the visitor's tail swept up by magnetic field lines and accelerated to tremendous velocities in the planet's radiation environment. Scientists puzzle over the precise outcome of this gravitational encounter, for the three-body dynamics involving Jupiter, the Sun, and the comet create a mathematically chaotic system where small uncertainties in initial conditions lead to vastly different final states. Monte Carlo simulations run thousands of possible scenarios, varying the comet's approach angle and velocity within observational uncertainties to map the probability distribution of outcomes. The mathematics reveal a sharp boundary between gravitational assist and gravitational capture, orbital destinies separated by margins measured in kilometers per second. The comet's approach geometry determines whether Jupiter's gravity acts as accelerator or deflector, the precise angle of closest approach governing whether the visitor gains or loses velocity in its passage around the gas giant. A gravity assist maneuver, the same technique used by spacecraft designers to reach the outer planets, could add several kilometers per second to the comet's velocity relative to the Sun, providing enough additional energy to ensure impact with Earth, despite the planet's modest gravitational cross-section. Conversely, a retrograde encounter might rob the comet of velocity, bending its hyperbolic trajectory into a long ellipse that carries it back toward interstellar space without approaching the inner solar system. Jupiter's Great Red Spot, a storm larger than Earth that has raged for centuries, rotates beneath the visitor's distant approach, with the slow majesty of atmospheric dynamics on planetary scales. The anticyclonic winds reach velocities exceeding 400 kilometers per hour, powered by the planet's internal heat and the Coriolis effect generated by Jupiter's rapid 10-hour rotation. This ancient tempest serves as a reminder of the gas giant's dynamic atmosphere, layers of hydrogen and helium that hide a core of rock and metallic hydrogen beneath thousands of kilometers of compressed gas. The comet's nucleus, still 20 kilometers of pristine interstellar ice, experiences Jupiter's tidal forces as differential acceleration across its elongated form. The Roche limit for such a loose aggregation lies well within Jupiter's cloud tops. But even at safe distances, the tidal gradient begins to stress the visitor's ancient structure. Cracks that formed during its ejection from its birth system now face forces they have not experienced in millions of years. Internal tensions that probe the fundamental cohesion of ice aged by cosmic radiation and thermal cycling. Radio telescopes detect the electromagnetic signature of the comet's interaction with Jupiter's magnetosphere, synchrotron radiation generated by charged particles spiraling along magnetic field lines. The characteristic frequency spectrum reveals the strength and geometry of the magnetic field, data that contributes to our understanding of Jupiter's internal structure and the dynamo process that generates its planetary magnetism. These radio emissions create a brief but intense burst of activity as the comet passes through the most energetic regions of the radiation belts. The irony accumulates across the decades of spaceflight Jupiter, humanity's gateway to the outer solar system through gravity assist maneuvers, now performs the same orbital mechanics on an interstellar visitor whose trajectory will determine Earth's fate. The same gravitational forces that accelerated Voyager, Galileo, and Cassini toward their distant targets now calculate the comet's destiny with mathematical precision. The gas giant serves as both shield and accelerator for the inner solar system, its massive presence determining which objects from deep space pose threats to the terrestrial planets. Asteroid 588 Achilles, the first discovered Trojan asteroid sharing Jupiter's orbit, maintains its position at the planet's L4 Lagrange point, even as the comet's passage creates minor perturbations in the gravitational field. These Trojan populations represent captured debris from the early solar system, primitive materials that have avoided both collisional evolution and thermal processing. Their stable orbital configuration demonstrates the power of gravitational resonances to preserve ancient arrangements across billions of years. Cosmic fossils locked in mathematical perpetuity. Jupiter's orbital velocity of 13 kilometers per second creates a substantial velocity difference with the approaching comet, relative motion, that determines the magnitude of gravitational acceleration during closest approach. The hyperbolic excess velocity, the comet's speed relative to Jupiter at infinite distance, combines with the planet's escape velocity to determine the deflection angle through conservation of energy and angular momentum. These fundamental principles of mechanics operate with the same precision, whether applied to spacecraft navigation or cosmic collision prediction. The gas giant's complex system of smaller moons, dozens of captured asteroids and fragments in eccentric orbits, bears witness to Jupiter's role as gravitational vacuum cleaner for the outer solar system. These irregular satellites, many with retrograde orbits that indicate capture rather than formation in place, demonstrate the planet's ability to alter the trajectories of small bodies from interstellar space. The comet now joins this procession of gravitational encounters, though its hyperbolic trajectory ensures escape rather than permanent capture. As the visitor rounds Jupiter's gravitational influence, its path either bends toward the inner solar system with increased velocity or curves away toward interstellar space with reduced energy. The outcome, determined by orbital mechanics established 4 centuries ago by Kepler and Newton, unfolds with mathematical inevitability. The comet emerges from Jupiter's sphere of influence, carrying either doom or deliverance for Earth, its trajectory now precisely calculated to intersect or miss our planet's orbit in the months ahead. Ground-based observatories track the comet's post-encounter trajectory with unprecedented precision. measuring tiny shifts in position against the background stars to determine whether Jupiter's gravity has set the visitor on a collision course with Earth. The data reveals the answer with growing certainty as successive observations refine the orbital elements, each measurement narrowing the uncertainty until the mathematical truth becomes undeniable. Only took Jupiter 4.5 billion years to grow into the solar system's gravitational guardian, and now its ancient mass renders final judgment on an interstellar visitor's approach toward our small blue world. The Kuiper Belt extends beyond Neptune's orbit like a frozen archive of the solar system's formation, a disk of primordial ice and rock that preserves the chemistry of the original solar nebula in temperatures so cold that molecular motion nearly ceases. Here, where sunlight arrives as pale as moonlight on Earth, Pluto and its companion Charon dance their eternal waltz, while thousands of smaller objects trace elliptical paths through the cosmic deep freeze. The comet's passage through this realm of perpetual winter marks its transition from interstellar wanderer to active solar system visitor, as the strengthening solar radiation begins to awaken processes that have slept for millions of years. Solar wind, that invisible stream of charge particles flowing outward from the sun's corona at 400 kilometers per second, begins to interact more substantially with the comet's growing coma as the visitor approaches the heliopore's boundary where solar influence meets interstellar medium. The wind carries embedded magnetic field lines that twist and reconnect in complex patterns, creating shock waves and plasma instabilities that accelerate particles to tremendous velocities. These energetic protons and electrons strike the comet's surface with increasing frequency, sputtering atoms and molecules into space through collision processes that operate like atomic-scale sandblasting. The comet's surface temperature, still hovering near -200 degrees Celsius, begins to rise measurably for the first time since its ejection from another stellar system. Infrared radiation from the distant sun penetrates the dark crust at a rate determined by the inverse square law, each halving of distance quadrupling the energy flux incident on the nucleus. This heating remains gentle by terrestrial standards, adding perhaps 10 degrees over the course of months, yet sufficient to trigger the first significant outgassing events, as volatile compounds sublimate directly from solid to gas without passing through liquid phase. Water ice, the dominant component of the comet's nucleus, requires temperatures above -150 degrees Celsius to sublimate at the low pressures of interplanetary space. Carbon monoxide and nitrogen ices, more volatile than water, begin their transformation to gas at even lower temperatures, creating the first substantial atmosphere around the nucleus. This tenuous coma spreads across thousands of kilometers, density so low it would qualify as laboratory vacuum on Earth, yet sufficient to scatter sunlight and create the first visible signs of the comet's awakening from its interstellar slumber. Scientists puzzle over the precise composition of this early outgassing, for spectroscopic analysis reveals molecular signatures both familiar and foreign to solar system chemistry. The isotopic ratios of hydrogen and deuterium suggest formation in a molecular cloud colder than our own solar nebula, while trace amounts of heavy water indicate neutron capture processes that occurred in the vicinity of a different stellar population. These chemical fingerprints provide direct evidence of the comet's alien origin, isotope signatures that could only have formed in the nuclear furnaces of stars whose light has never illuminated Earth's surface. The visitor's rotation period, approximately 27 hours, creates a complex pattern of heating and cooling as different regions of the nucleus alternately face toward and away from the sun. This thermal cycling produces jets of gas and dust that emerge from specific locations on the surface, creating asymmetric outgassing that acts like a weak rocket engine. The non-gravitational forces generated by these jets can alter the comet's trajectory in unpredictable ways, small accelerations that accumulate over time to change the precise timing and geometry of its approach to Earth. Kuiper Belt objects, those remnant planetesimals that never accreted into full planets, maintain their ancient orbits with the patience of geological time. Haumea, and Eris trace their elongated ellipses through the outer darkness. Worlds of ice and rock that preserve the original inventory of volatile compounds from the early solar system. The comet's passage creates no meaningful gravitational disturbance among these distant objects, yet their presence serves as testament to the processes that shaped our stellar neighbourhood during its violent youth. The comet's coma begins to develop internal structure as solar radiation pressure separates different molecular species according to their mass and absorption properties. Water molecules, with their strong absorption in the ultraviolet, experience greater radiation pressure than heavier compounds, creating a compositional gradient within the expanding gas cloud. This differential acceleration leads to the formation of distinct shells and streamers within the coma, visible only through sophisticated spectroscopic analysis that can isolate the emission lines of individual molecular species. Plasma interactions between the solar wind and the comet's ionosphere create the first hints of a magnetic tail. Charged particles swept away from the nucleus by the embedded magnetic field in the solar wind. Unlike the dust tail that will form later, this plasma tail remains invisible to optical observation, detectable only through radio emissions generated by accelerated electrons spiraling along magnetic field lines. The tail points directly away from the sun regardless of the comet's motion, a compass needle aligned with the radial flow of solar wind through the planetary system. The irony unfolds across interplanetary distances. The same solar radiation that nurtures life on Earth now begins to destroy this visitor from another star, gradually subliming away the ice that has preserved alien chemistry for millions of years. The comet's death begins slowly in the cold depths beyond Neptune, a process that will accelerate dramatically as it approaches the inner solar system, where solar heating becomes intense enough to strip away tons of material per hour from its ancient surface. Trans-Neptunian objects scattered by gravitational encounters with the giant planets maintain highly elliptical orbits that carry them from the Kuiper belt to distances exceeding 100 astronomical units. These scattered disk objects preserve in their orbital elements the gravitational history of the outer solar system, evidence of planetary migration and resonance sweeping that occurred during the late heavy bombardment 4 billion years ago. The comet's hyperbolic trajectory cuts across this population of gravitational exiles. Interstellar visitor meeting local outcasts in the cold reaches beyond planetary influence. Radio observations detect the strengthening emissions from the comet's growing coma, hydroxyl radicals and other molecular fragments created by the photodissociation of water vapor in the solar ultraviolet field. These characteristic frequencies serve as beacons that allow astronomers to track the comet's composition and activity level as it approaches the inner solar system. The radio spectrum reveals not only the abundance of different molecular species, but also their excitation temperature and velocity distribution, data that constrains models of coma formation and evolution. The comet's albedo, the fraction of incident sunlight it reflects, remains extremely low due to the organic compounds that darken its surface through billions of years of cosmic ray bombardment. This dark coloration, similar to charcoal, ensures efficient absorption of solar heating while minimizing the reflection that might help preserve the nucleus against thermal processing. The visitor's surface properties thus accelerate its own destruction. Dark materials that guarantee maximum energy absorption from our star's radiation. As the comet crosses the orbit of Neptune, 30 astronomical units from the Sun, its transformation from inactive nucleus to active comet becomes irreversible. The coma now spans tens of thousands of kilometers, approaching the size of a terrestrial planet. While mass loss rates climb toward kilograms per second, this material, ejected at velocities exceeding the nucleus's escape velocity, forms an expanding cloud of gas and dust that will soon become visible to Earth-based telescopes as a fuzzy star moving against the background constellations. Ground-based observatories begin their systematic monitoring campaign, measuring the comet's brightness and spectroscopic signature at regular intervals to track its evolution as solar heating intensifies. These observations provide crucial data for predicting the visitor's behavior during its passage through the inner solar system, information that could determine whether fragments will survive atmospheric entry if the trajectory leads toward Earth impact, only took the Kuiper belt 4.5 billion years to settle into its current configuration after the orbital migration of the giant planets. And now this ancient reservoir of primordial ice witnesses the transformation of an interstellar visitor as it awakens from its million-year slumber, trading the chemistry of another star for dissolution in our Sun's radiation field. Mars orbits the Sun at a distance of 1.5 astronomical units, a rusty world of iron oxide dust and polar ice caps that bears the scars of an ancient atmospheric catastrophe. The red planet's thin atmosphere, less than 1% of the density of Earth's, offers no meaningful protection against the cosmic forces that now ripple through the inner solar system as the interstellar visitor approaches. Mars sits in its elliptical orbit with the stoic patience of a world that has already endured 4 billion years of solar wind erosion, its magnetic field long since extinguished by the cooling of its molten core, leaving only weak crustal magnetism to mark where a global dynamo once operated. The comet's gravitational influence reaches across the void to touch Mars with invisible fingers, perturbations so minute they require the most precise orbital measurements to detect. The planet's two small moons, Phobos and Deimos, experience microscopic changes in their orbital periods as the visitor's mass creates temporary modifications in the gravitational field that binds them to their primary. These captured asteroids, probably refugees from the nearby asteroid belt, maintain their close orbits through gravitational forces that measure in the millions of newtons. Yet even these substantial attractions yield to the subtle mathematics of three-body orbital dynamics. The Martian atmosphere, composed primarily of carbon dioxide with traces of nitrogen and argon, exists in a delicate equilibrium between sublimation from the polar ice caps and loss to space through atmospheric sputtering. Solar wind particles, unimpeded by any substantial magnetic field, strike the upper atmosphere directly and accelerate molecules to escape velocity, a process that has stripped away most of Mars's original atmosphere over geological time. The planet loses approximately 100 grams of atmosphere per second, a rate so gradual it would take billions of years to make measurable changes, yet inexorable in its cumulative effect. Scientists puzzle over the precise gravitational effects as the comet's approach creates resonant perturbations in Mars's orbital elements, tiny changes in eccentricity and inclination that will propagate through millions of years of planetary motion. The red planet's orbit already varies on cycles lasting hundreds of thousands of years. Milankovitch variations that control the sublimation of polar ice and the global redistribution of dust through massive planet-wide storms. These orbital cycles have governed Martian climate for eons, determining whether the poles accumulate ice or release water vapor to the thin atmosphere. The planet's surface bears witness to catastrophic events that shaped its evolution during the solar system's violent youth. Olympus Mons, largest volcano in the solar system, rises 27 kilometers above the surrounding plains, a monument to the volcanic activity that once resurfaced vast regions of the planet. The Tharsis volcanic province, containing 4 massive shield volcanoes, represents billions of years of intermittent eruptions that may have episodically thickened the atmosphere and created temporary greenhouse conditions capable of sustaining liquid water on the surface. Valles Marineris, the Grand Canyon of Mars, stretches across thousands of kilometers of the planet's equatorial region, a tectonic scar created by the same crustal stresses that built the Tharsis Bulge. This enormous rift system exposes billions of years of Martian geological history in its layered walls, sedimentary deposits that record ancient climate cycles and possible episodes of surface water activity. The canyon's depth exceeds 7 kilometers in places, creating pressure differentials that allow liquid water to exist briefly even under current atmospheric conditions. The comet's growing coma, now expanding across millions of kilometers as increased solar heating drives sublimation rates higher, begins to scatter sunlight in ways detectable by Mars-based instruments. Robotic rovers and orbital satellites record subtle changes in the zodiacal light, the faint glow created by sunlight reflecting off interplanetary dust. These observations provide ground truth for models of comet evolution and dust production rates, calibrating the theoretical frameworks used to predict the visitor's behavior during its approach to Earth. Martian polar ice caps, composed of both water ice and frozen carbon dioxide, undergo seasonal cycles that transport vast quantities of material between the northern and southern hemispheres. During winter, carbon dioxide condenses directly from the atmosphere to form dry ice deposits several meters thick, while summer sublimation returns this material to gaseous form and creates the pressure variations that drive the planet's weather patterns. The permanent water ice caps, buried beneath seasonal CO2 deposits, contain enough frozen water to create a global ocean several meters deep if melted and distributed evenly across the surface. The irony settles across interplanetary distances Mars, a world that may have once harboured conditions suitable for life, now serves as passive observer to the approach of material from another stellar system. The red planet's geological record suggests episodes of surface water activity, river valleys and lake beds that indicate a warmer, denser atmosphere during the solar system's first billion years. Yet the same solar wind that now carries news of the comet's approach also contributed to the atmospheric loss that transformed Mars from potentially habitable world to frozen desert. Impact craters pepper the Martian surface with the accumulated scars of 4 billion years of bombardment, each circular scar marking a collision event that excavated millions of tons of rock and temporarily modified the local environment. The largest of these impacts, the Hellas Basin, stretches across 2,000 kilometers and reaches depths of 9 kilometers below the mean surface level. These ancient collisions provide analogues for understanding the effects of comet impact. Though none represents material from interstellar space, Mars's eccentric orbit carries it from 1 1/3 to 1 2/3 astronomical units from the Sun, a variation that creates substantial differences in solar heating between perihelion and aphelion. This orbital eccentricity, combined with the planet's obliquity of 25 degrees, drives complex climate cycles that control the global redistribution of dust and ice. During southern summer, when Mars reaches perihelion, increased heating often triggers global dust storms that can obscure the entire planet for months at a time. The planet's rotational period of 24 hours and 37 minutes creates Earth-like day-night cycles. Though the thermal inertia of the thin atmosphere provides little moderation of temperature extremes, surface temperatures can vary by more than 100 degrees Celsius between day and night. Thermal cycling that contributes to the physical weathering of surface rocks through repeated expansion and contraction. This mechanical weathering, combined with chemical oxidation, has created the iron oxide dust that gives Mars its characteristic red coloration. Atmospheric dynamics on Mars operate under conditions alien to terrestrial experience. Pressure so low that liquid water cannot exist stably on most of the surface, despite temperatures that sometimes rise above freezing. The triple point of water, that unique combination of temperature and pressure where liquid, solid, and gas phases can coexist, occurs only in the deepest basins and impact craters, where atmospheric pressure exceeds the critical 611 pascals required for liquid stability. As the comet continues its mathematical approach toward the inner solar system, Mars maintains its ancient orbit with the reliability of celestial mechanics, a world whose surface features record the history of planetary evolution under conditions markedly different from Earth. The red planet's thin atmosphere and lack of magnetic field create an environment where cosmic radiation reaches the surface unimpeded, conditions that would prove lethal to unprotected terrestrial life, yet may harbour subsurface ecosystems adapted to extreme environments. The Martian magnetosphere, consisting only of weak crustal magnetic fields rather than a global dipole, provides no coherent deflection of solar wind or cosmic rays. These remnant magnetic patches, strongest in the ancient highland terrain of the southern hemisphere, suggest that Mars once possessed a global magnetic field similar to Earth's, but lost it early in planetary history as the core cooled and solidified. The absence of magnetic protection has allowed solar wind to strip away most of the original atmosphere, leaving behind the tenuous gas envelope that barely qualifies as an atmosphere by terrestrial standards. Only took Mars 4.5 billion years to evolve from potentially habitable world to frozen desert. And now this ancient planet watches the approach of an interstellar visitor whose trajectory may soon test whether Earth can maintain the atmospheric and magnetic protection that Mars lost long ago. The Moon drifts through space at a distance of 384,000 kilometers from Earth, locked in gravitational embrace with its primary through tidal forces that have operated for 4.5 billion years. This ancient partnership, born from the collision that may have created both bodies during the solar system's violent youth, now faces subtle perturbations as the interstellar visitor's approach begins to influence the delicate orbital mechanics of the Earth-Moon system. The lunar surface, airless and unprotected by any magnetic field, receives the full intensity of cosmic radiation and solar wind, preserving in its regolith the accumulated history of every particle that has struck it across geological time. The comet's gravitational influence, still relatively weak at distances measured in millions of kilometers, creates minute changes in the Moon's orbital velocity that require laser ranging experiments to detect. Retroreflectors placed on the lunar surface by Apollo astronauts and Soviet robotic missions allow scientists to measure the Earth-Moon distance with millimeter precision, tracking variations in the satellite's position that reveal the subtle effects of external gravitational perturbations. These measurements show fluctuations in the Moon's orbit as the visitor's mass temporarily modifies the gravitational field that has maintained lunar stability for eons. Mare Tranquillitatis, the Sea of Tranquility where humans first touched another world, stretches across hundreds of kilometers of basaltic lava flows that erupted during the Moon's volcanic youth 3.5 billion years ago. These ancient seas, formed when asteroid impacts fractured the lunar crust and allowed molten rock to flood the resulting basins, now serve as archives of early solar system bombardment rates. The dark maria contain impact glasses and breccias that record the composition of the asteroids and comets that pummeled the inner solar system during the late heavy bombardment. The Moon's synchronous rotation, with one hemisphere perpetually facing Earth while the other remains forever hidden, results from tidal locking that occurred early in lunar history when the satellite orbited much closer to its primary. This gravitational coupling ensures that the same lunar features have watched over Earth for billions of years, the familiar patterns of Maria and Highlands serving as humanity's celestial timekeeper. Yet the Moon continues to recede from Earth at a rate of 3.5 centimeters per year, gradually lengthening both the lunar month and Earth's day as angular momentum transfers from planetary rotation to orbital motion. Scientists puzzle over the precise effects of the comet's approach on the complex lunar librations, the gentle nodding and swaying motions that allow terrestrial observers to glimpse slightly more than half the lunar surface over time. These oscillations result from the interplay between the Moon's elliptical orbit and its uniform rotation, creating apparent motions that vary by several degrees in longitude and latitude. The visitor's gravitational field introduces additional perturbations into this already complex system, modifications that could alter the lunar libration pattern in ways that persist long after the comet has departed the inner solar system. The lunar far side, shielded from Earth's radio emissions and permanently turned away from terrestrial civilization, offers the quietest electromagnetic environment in the inner solar system. Radio telescopes on the Moon's hidden hemisphere could detect signals impossible to observe from Earth's surface, where interference from human technology and ionospheric disturbances mask faint cosmic radio sources. This natural radio quiet zone represents one of the Moon's most valuable scientific resources, a platform for astronomical observations unconstrained by terrestrial interference. Lunar impact craters, ranging from microscopic pits in individual rock samples to basins thousands of kilometers across, preserve the complete history of bombardment in the inner solar system. The South Pole Aitken Basin, largest and oldest recognizable impact structure on the Moon, stretches across 2,000 kilometers of the lunar far side and penetrates deep enough into the crust to excavate material from the lunar mantle. These ancient scars provide calibration points for understanding impact processes and crater formation mechanisms that apply throughout the solar system. The Moon's internal structure, revealed by seismic experiments deployed during Apollo missions, shows evidence of a small iron core surrounded by a thick mantle of olivine and pyroxene. Moon quakes, triggered by tidal stresses and thermal expansion, occur with monthly periodicity that reflects the changing gravitational forces as the Moon follows its elliptical orbit. The seismic data reveals a partially molten zone at the core mantle boundary, suggesting that lunar differentiation may be incomplete despite 4.5 billion years of cooling. The irony accumulates across astronomical distances. The Moon, Earth's constant companion that has stabilized our planet's axial tilt and moderated climate variations for billions of years, now experiences gravitational perturbations from material that formed in orbit around another star. The satellite that may have made complex life possible on Earth through its climate-stabilizing influence faces forces that could minutely alter its protective embrace. Though any changes would occur too gradually for immediate detection, lunar dust, pulverized by billions of years of micrometeorite bombardment in the absence of atmospheric protection, creates a regolith layer tens of meters deep across most of the surface. This fine-grained material, electrostatically charged by solar-wind interactions, presents unique challenges for future lunar exploration as it adheres to equipment and poses health hazards for astronauts. The dust particles, angular and sharp due to the lack of erosion processes, preserve the chemical composition of the original bedrock while recording the isotopic signatures of solar wind implantation. The comet's growing coma and tail become visible to lunar-based observers as a fuzzy patch moving against the background stars, unobscured by atmospheric scintillation or light pollution that degrades terrestrial observations. Automated telescopes on the lunar surface track the visitor's approach with unprecedented precision, measuring changes in brightness and spectral characteristics that reveal the evolving composition of the outgassing nucleus. These observations provide crucial data for predicting the comet's behavior as it approaches Earth's gravitational sphere of influence. Tidal forces between Earth and Moon, responsible for oceanic tides and the gradual slowing of planetary rotation, now face additional complexity as the comet's gravity introduces three-body effect into the previously stable two-body system. The visitor's mass, though small compared to Earth or Moon, creates perturbations that propagate through the tidal bulge and modify the energy dissipation that has driven lunar recession for eons. These effects remain subtle, measurable only through decades of precise observations, yet they represent the first external influence on Earth-Moon dynamics since the system achieved its current configuration. Lunar volcanic activity, which ceased approximately 1 billion years ago as the Moon's interior cooled below the threshold for magma generation, left behind a complex history recorded in the isotopic compositions of returned samples. The youngest mare basalts show evidence of prolonged differentiation processes that concentrated radioactive elements and rare earth metals in the final stages of lunar volcanism. These late-stage magmas provide windows into the deep lunar interior and the processes that governed planetary cooling in small rocky bodies. The Moon's lack of atmosphere and magnetic field creates surface conditions where cosmic ray bombardment proceeds unimpeded, generating nuclear reactions that produce characteristic isotopes in the upper layers of lunar rocks. These cosmic ray exposure ages provide precise dating for surface features and reveal the flux history of energetic particles in the inner solar system. The lunar regolith serves as a passive detector that has recorded billions of years of cosmic ray variations, including possible signatures from nearby supernova explosions and solar flares. As the comet approaches the 1 astronomical unit distance that defines Earth's orbit, the Moon maintains its patient revolution around its primary, completing one orbit every 27 1/3 days with the reliability that has made it humanity's oldest chronometer. The lunar phases, controlled by the changing geometry of Sun-Earth-Moon angles, continue their ancient cycle, while the visitor's approach adds new variables to the gravitational equations that govern satellite motion. Lunar laser ranging data reveals fluctuations in the Earth-Moon distance that encode information about both terrestrial and lunar internal structure, tidal dissipation rates, and relativistic effects predicted by Einstein's theory of general relativity. These measurements, accurate to millimeters across hundreds of thousands of kilometers, represent one of the most precise tests of gravitational theory available to experimental science. The comet's approach introduces additional terms into these already complex equations. Gravitational perturbations that test our understanding of celestial mechanics under conditions not experienced since the solar system's formation. Only took the Earth-Moon system 4.5 billion years to evolve from a chaotic post-collision environment to the stable configuration that has protected Earth's climate and enabled the evolution of complex life. And now this ancient partnership faces gravitational influences from beyond the solar system as an interstellar visitor approaches the final phases of its hyperbolic trajectory. The magnetosphere extends Earth's protective influence far into space, an invisible shield generated by the planet's molten iron core and shaped by the constant pressure of solar wind into a teardrop configuration that stretches beyond the Moon's orbit. This magnetic cocoon has deflected charged particles and cosmic radiation for billions of years, creating the stable environment that allows complex chemistry and biology to flourish on the surface below. Now the interstellar visitor approaches this boundary, its nucleus still intact but surrounded by an expanding coma of gas and dust that will soon encounter the magnetic field lines and plasma populations that guard Earth's atmospheric envelope. The bow shock, that invisible boundary where Earth's magnetosphere meets the supersonic solar wind, ripples with electromagnetic turbulence as the comet's ionized coma begins to interact with the planet's magnetic environment. Charged particles from the visitor's subliming nucleus encounter magnetic field strengths measured in nanoteslas, forces that seem negligible yet prove sufficient to deflect individual ions and electrons along complex spiral trajectories. The comet's plasma tail, already streaming away from the nucleus under solar wind pressure, now faces the additional complexity of Earth's magnetospheric currents and field-aligned particle precipitation. Van Allen radiation belts, those toroidal regions where Earth's magnetic field traps high-energy particles in stable orbits, begin to experience perturbations as the comet's approach modifies the global configuration of magnetic field lines. These belts, discovered during the early space age and mapped by generations of scientific satellites, contain protons and electrons with energy sufficient to damage electronic systems and pose hazards to astronauts. The visitor's ionized coma introduces new particle populations into this radiation environment, cosmic ray secondaries and solar energetic particles that have been accelerated by magnetic reconnection events in the comet's plasma tail. Atmospheric entry begins at an altitude of 100 kilometers above Earth's surface, the Kármán line that marks the arbitrary boundary between atmosphere and space. Here, where atmospheric density remains less than 1/1,000,000th of sea level pressure, the comet's nucleus encounters the first significant resistance to its hyperbolic trajectory. Molecules of nitrogen and oxygen, though sparse at this altitude, begin to impact the visitor's surface at velocities exceeding 50 kilometers per second, each collision transferring kinetic energy that manifests as heat through the fundamental physics of momentum conservation. Scientists puzzle over the precise sequence of events as the 20-kilometer nucleus encounters atmospheric drag for the first time in its interstellar journey. Forces that have played no role in its million-year passage through the vacuum between stars. Computer models struggle to predict the behavior of such exotic ice under extreme heating rates. Material properties that cannot be replicated in terrestrial laboratories, where pressure and temperature combinations remain within human experience. The comet's interior structure, weakened by billions of years of cosmic ray bombardment, now faces thermal stresses that may trigger catastrophic fragmentation. The thermosphere, that region between 80 and 600 kilometers altitude where temperature rises with altitude due to solar ultraviolet absorption, provides the first substantial interaction between Earth's atmosphere and the visitor's expanding coma, atomic oxygen, the dominant species at these altitudes, reacts chemically with water vapor and other molecules subliming from the comet's surface, creating exotic compounds that have never existed in Earth's atmosphere. These chemical reactions release additional energy that contributes to the heating and fragmentation of the nucleus. Auroral displays begin to appear at high latitudes as the comet's magnetic field interacts with Earth's magnetosphere. Charged particles following field lines down into the polar atmosphere where they collide with nitrogen and oxygen molecules to create spectacular light shows. These auroras differ from typical solar-driven phenomena in their spectral characteristics, showing emission lines from exotic molecular species that originate in the comet's coma rather than the solar wind. The colours shift through wavelengths rarely seen in terrestrial auroras, greens and reds produced by forbidden transitions in atoms excited by the unique chemistry of interstellar ice. The mesosphere, that middle atmospheric layer where temperature decreases with altitude and meteors typically burn up during atmospheric entry, experiences unprecedented heating rates as fragments of the comet begin to separate from the main nucleus. These pieces, ranging from boulders to mountains in size, create brilliant fireballs that outshine Venus as they streak across the night sky at velocities that dwarf typical meteoroid impacts. The optical displays visible from Earth's surface represent only a fraction of the total energy being released, most dissipated as infrared radiation and shock-wave heating of the surrounding atmosphere. Seismic stations around the globe detect the first atmospheric pressure waves generated by the comet's passage through the upper atmosphere. Infrasonic signals that propagate through the atmosphere at the speed of sound. These acoustic signatures, similar to those generated by nuclear explosions but orders of magnitude more powerful, circumnavigate the planet multiple times as pressure disturbances reflect off atmospheric layers and interfere constructively and destructively. The infrasonic energy carries information about the breakup dynamics and total energy release that supplements optical observations. The irony unfolds across atmospheric layers Earth's protective atmosphere, the same gaseous envelope that has shielded the surface from cosmic bombardment for billions of years, now serves as the agent of the comet's destruction. The visitor that has survived the vacuum of interstellar space intact now faces disintegration by collision with molecules so sparse they would qualify as laboratory vacuum by terrestrial standards. The atmosphere demonstrates its protective power through the violence of its resistance to high-velocity intrusion. Noctilucent clouds, those high-altitude ice crystal formations that occur in the mesosphere during summer months, experience disruption as shock waves and thermal radiation from the comet's passage alter the temperature and particle environment at these altitudes. The delicate balance of ice nucleation and sublimation that creates these ethereal displays faces conditions outside any previous atmospheric experience. Water vapor concentrations and heating rates that transform the mesospheric environment in ways that may persist for months after the comet's passage. Radio communications around the globe experience blackouts as the ionosphere, that electrically conducting layer between 60 and 1,000 kilometers altitude, becomes overloaded with free electrons and ions created by the comet's interaction with atmospheric gases. The normal E and F layers that reflect radio waves and enable long-distance communication suffer disruption as extreme ionization rates create plasma densities far exceeding typical solar activity levels. Satellite navigation systems lose accuracy as signal propagation through the disturbed ionosphere introduces unpredictable delays and phase shifts. The stratosphere, normally isolated from space weather effects by the overlying atmospheric layers, begins to experience heating from infrared radiation emitted by the glowing debris cloud created as the comet fragments. This thermal input, unprecedented in atmospheric science, threatens to disrupt the ozone layer through enhanced photochemical reaction rates and altered circulation patterns. Temperature increases measured in tens of degrees could persist for months as the energy slowly redistributes through atmospheric motion and radiative cooling. Atmospheric chemistry models struggle to predict the cascade of reactions triggered by the injection of interstellar material into Earth's gas envelope. Exotic molecular species that have never participated in terrestrial atmospheric chemistry. Water isotopomers with different deuterium ratios. Carbon compounds bearing isotopic signatures from another stellar system. And noble gas isotopes produced by cosmic ray bombardment during the comet's interstellar journey now mix with terrestrial atmospheric gases in proportions and at rates that challenge existing chemical kinetics databases. As fragments of the nucleus penetrate deeper into the atmosphere, their surfaces ablate at rates measured in centimeters per second. Material stripped away by aerodynamic forces and deposited as a trail of glowing plasma extending across hundreds of kilometers of the upper atmosphere. This ablated material, rich in organic compounds and water vapor, creates artificial meteor streams that persist for hours as the debris continues to interact with atmospheric gases at velocities still measured in tens of kilometers per second. Ground-based observatories track the comet's atmospheric entry with unprecedented precision. Spectroscopic measurements that reveal the real-time composition of material subliming from the nucleus as it encounters increasing atmospheric density. These observations provide direct samples of interstellar chemistry, isotope ratios and molecular abundances that encode the history of stellar nucleosynthesis in the comet's birth system. The data represents humanity's first direct chemical analysis of matter from another star. Only took Earth's atmosphere 4 billion years to evolve from a reducing environment dominated by methane and ammonia to the oxygen-rich mixture that sustains complex life. And now this protective envelope faces the challenge of absorbing and dissipating the kinetic energy of an interstellar visitor whose hyperbolic trajectory carries the accumulated gravitational potential of its entire galactic journey. The mesosphere embraces the disintegrating comet at an altitude of 80 kilometers above Earth's surface, where atmospheric density remains 10,000 times thinner than sea level, yet proves sufficient to begin the violent process of aerodynamic heating that will transform interstellar ice into incandescent plasma. This region, coldest in Earth's atmosphere with temperatures dropping to minus 90 degrees Celsius, suddenly experiences thermal conditions more extreme than the surface of the Sun as fragments of the comet's nucleus compress the sparse air ahead of them into shock waves that glow with the intensity of stellar cores. The mesosphere, typically host only to noctilucent clouds and the occasional meteor, now witnesses the complete annihilation of matter that has travelled between star systems. Shockwave physics dominate the interaction between comet fragments and atmospheric molecules, each piece of nucleus creating a bow shock where compressed air reaches temperatures exceeding 10,000 degrees Celsius. At these velocities, normal concepts of melting and vaporization become irrelevant as solid matter transitions directly to plasma through collision processes that strip electrons from atomic nuclei. The resulting ionized gas glows across the entire electromagnetic spectrum, from radio waves to gamma rays, creating fireballs visible from thousands of kilometers away despite occurring in the rarefied upper atmosphere. Meteor showers of unprecedented scale illuminate the night sky as thousands of fragments separate from the main nucleus, each following its own ballistic trajectory through the atmosphere, while contributing to a collective light show that outshines the full moon. These fragments, ranging from pebbles to city blocks in size, create persistent trains of glowing plasma that linger for minutes in the thin mesospheric air. The visual spectacle represents only a fraction of the total energy release, most dissipated as infrared radiation and kinetic heating of atmospheric gases, rather than visible light detectable by human observers. The comet's breakup follows complex fluid dynamics, as aerodynamic forces overcome the weak gravitational binding that has held the nucleus together for millions of years. Differential atmospheric drag creates torques that spin individual fragments into chaotic tumbling motions, while pressure gradients across the irregular surfaces generate forces that tend to separate the loosely bound aggregation of ice and rock. The fragmentation proceeds in cascading stages, large pieces splitting into smaller ones until the entire nucleus dissolves into a cloud of debris spanning hundreds of kilometers. Scientists puzzle over the precise mechanisms of atmospheric interaction for materials that have never experienced such conditions. Ice compositions and internal structures that formed under the influence of another star's radiation and interstellar chemistry. Laboratory experiments cannot replicate the combination of extreme velocity, exotic composition, and pristine structural properties that characterize this interstellar visitor. Computer simulations based on terrestrial materials provide only rough approximations of the actual physics governing the comet's atmospheric encounter. Each fragment creates its own trail of ablated material, atoms and molecules stripped from the surface by aerodynamic heating and deposited along the trajectory as a glowing wake of plasma. These ablation trails contain the chemical fingerprints of another stellar system, isotope ratios and molecular abundances that provide direct evidence of nucleosynthesis, processes that occurred in different galactic environments. Spectroscopic analysis of the glowing trails reveals deuterium enhancement, carbon-13 anomalies, and noble gas compositions that confirm the comet's extrasolar origin. The mesosphere's normal temperature structure, maintained by the balance between solar heating and radiative cooling, faces complete disruption as shock waves and thermal radiation from the fragmenting comet deposit unprecedented amounts of energy into this atmospheric layer. Temperature increases measured in hundreds of degrees propagate through mesospheric winds, creating circulation patterns unlike anything an atmospheric science experience. The thermal disturbance may persist for months as the excess energy slowly redistributes through atmospheric motion and radiation to space. Atmospheric chemistry undergoes radical transformation as exotic molecules from interstellar space mix with terrestrial gases under conditions of extreme temperature and ionization. Water molecules bearing different isotopic compositions than terrestrial water participate in reactions that have never occurred in Earth's atmosphere, while organic compounds synthesized in the vicinity of another star contribute carbon, nitrogen, and sulfur in ratios alien to terrestrial biochemistry. The resulting chemical soup contains molecular species that exist nowhere else in the solar system. Radio emissions generated by the plasma cloud create electromagnetic signatures detectable by ground-based receivers. Synchrotron radiation produced by electrons accelerating in the magnetic fields generated by the current systems in the ionized gas. These radio bursts occur across a broad frequency spectrum, from very low-frequency waves that propagate in the Earth ionosphere waveguide to microwave emissions that penetrate the atmosphere with minimal attenuation. The radio signatures provide real-time diagnostics of plasma temperature, density, and magnetic field strength. The irony burns across atmospheric layers, the mesosphere, Earth's coldest atmospheric region, and a natural barrier that protects the lower atmosphere from most cosmic debris, now experiences temperatures hot enough to vaporize any known material. This thermal environment, created by the collision between interstellar matter and terrestrial air, briefly recreates conditions similar to stellar interiors where nuclear fusion processes synthesize heavy elements from hydrogen and helium. The comet's destruction generates a temporary star in Earth's upper atmosphere. Infrasonic waves generated by the explosive fragmentation propagate downward through the atmosphere. Pressure oscillations powerful enough to shatter windows and trigger seismic instruments on the surface below. These acoustic signatures travel at the speed of sound through atmospheric layers, reflecting off temperature and density boundaries to create complex interference patterns that carry information about both the breakup dynamics and atmospheric structure. The infrasonic energy represents a small fraction of the total kinetic energy being dissipated, yet proves sufficient to create globally detectable atmospheric disturbances. Noctilucent clouds, those delicate ice crystal formations that normally grace the mesosphere during summer months at high latitudes, face instant vaporization in the thermal environment created by the comet's passage. The shock waves and radiation fields destroy not only existing cloud formations, but also alter the nucleation conditions that allow ice crystals to form in the mesospheric environment. Recovery of normal noctilucent cloud activity may require months as atmospheric temperatures and aerosol populations return to their typical values. The stratosphere below begins to experience heating from infrared radiation emitted by the glowing debris cloud, thermal input that threatens the delicate ozone chemistry, responsible for shielding Earth's surface from harmful ultraviolet radiation. Temperature increases in the lower stratosphere could enhance ozone destruction rates while altering circulation patterns that normally isolate polar and tropical atmospheric regions. The stratospheric response represents one of the longer-lasting atmospheric effects of the comet's passage. Each second of the comet's atmospheric transit converts millions of tons of solid matter into plasma and vapor, mass loss rates that exceed the combined flow of all terrestrial rivers. The energy release approaches that of large volcanic eruptions, though concentrated into a much briefer time interval and deposited directly into the upper atmosphere rather than the surface environment. This energy dissipation rate creates local heating sufficient to dissociate molecular nitrogen and oxygen into their constituent atoms. Ground-based cameras capture the breakup sequence in unprecedented detail, high-speed photography that reveals the fluid dynamics of fragmenting ice under extreme aerodynamic loading. The images show how individual pieces separate from the main mass, their trajectories influenced by both gravitational acceleration and aerodynamic forces that vary with fragment size and shape. These visual records provide crucial validation for theoretical models of comet fragmentation in planetary atmospheres. Satellite instruments detect the infrared signature of the event from orbit, thermal emissions that reveal the temperature distribution within the debris cloud and the rate at which energy radiates to space. The infrared observations complement optical measurements by providing information about the total energy budget and the efficiency of different radiative cooling processes. These space-based measurements avoid atmospheric absorption that limits ground-based infrared astronomy. The comet's final moments as a coherent object unfold with the violence of stellar processes compressed into human timescales. Millions of years of interstellar preservation ending in minutes of atmospheric destruction. The nucleus that has maintained its structural integrity across the gulf between star systems now surrenders to the mathematical inevitability of fluid dynamics, shockwave physics that reduce solid matter to constituent atoms through collision processes more violent than those occurring in stellar chromospheres. Only took the mesosphere 4 billion years to develop its characteristic temperature and density structure through the balance of solar heating and radiative cooling. And now this atmospheric layer experiences thermal conditions unprecedented in terrestrial atmospheric science, as interstellar matter delivers the accumulated kinetic energy of its galactic journey into the rarefied gases that protect Earth's surface from cosmic bombardment. The Pacific Basin stretches across 1/3 of Earth's surface, a vast expanse of water whose deepest trenches plunge 11 kilometers below sea level into abyssal darkness that has never known sunlight. This oceanic realm, largest geographic feature on the planet, now faces the mathematical certainty of impact as computer models calculate trajectory solutions for the largest fragments surviving atmospheric breakup. The ocean's 4 billion cubic kilometers of water, heated by submarine volcanism and stirred by currents that transport equatorial warmth toward polar regions, presents a target so vast that collision becomes statistically inevitable despite the comet's fragmentation in the mesosphere above. Tsunami generation follows the physics of impulsive water displacement. Energy transfer that occurs when solid matter traveling at hypersonic velocities encounters the ocean's surface with forces measured in megatons of TNT equivalent. The impact creates a cavity in the water column that extends to the seafloor, temporarily exposing sections of ocean bottom before gravitational restoration generates the initial wave train that will propagate across the basin at velocities approaching jet aircraft speeds. These waves, barely perceptible in deep water but capable of devastating coastal regions, carry the kinetic energy of interstellar motion converted to fluid dynamics through the conservation laws that govern all mechanical systems. The Mariana Trench, deepest point on Earth's surface and home to extremophile organisms that thrive under pressure conditions exceeding those at the center of small moons, lies within the potential impact zone defined by orbital mechanics and atmospheric fragmentation models. This abyssal environment, where pressure reaches over 1,000 times sea level atmospheric pressure and temperatures hover near freezing despite proximity to the planet's molten interior, hosts unique ecosystems based on chemosynthesis rather than photosynthesis. These communities, sustained by sulfur compounds emerging from hydrothermal vents, represent Earth's closest analogues to possible life in the subsurface oceans of Europa and Enceladus. Scientists puzzle over the precise energy partition during oceanic impact. Complex physics that involve shockwave propagation through both water and underlying crustal rock, cavity formation, and collapse dynamics that have been studied primarily through nuclear weapons testing and asteroid impact experiments. The comet fragments, still travelling at velocities exceeding 20 km per second despite atmospheric deceleration, carry kinetic energies that dwarf the largest nuclear weapons ever detonated. Computer simulations suggest that impact into deep ocean water might actually enhance the devastating effects by coupling energy more efficiently into tsunami generation than impact onto solid land. Seismic waves generated by seafloor impact propagate through Earth's crust at velocities determined by the elastic properties of rock. Compressional waves that arrive at distant seismic stations minutes before the surface waves that cause the most destructive ground motion. These P waves, travelling at 8 km per second through the mantle, provide the first global indication of impact magnitude and location, data that tsunami warning systems use to calculate wave arrival times at threatened coastlines. The seismic signature differs from typical earthquakes in its impulsive character and the broad frequency spectrum generated by the near-instantaneous energy release. The Ring of Fire, that belt of volcanic activity surrounding the Pacific Basin, where tectonic plates converge and create the conditions for explosive eruptions, faces additional stress as impact-generated seismic waves propagate through already unstable crustal regions. Fault systems that have accumulated strain for decades or centuries might find their equilibrium disrupted by the passage of seismic energy, potentially triggering cascading sequences of earthquakes and volcanic eruptions that extend the impact's effects far beyond the immediate blast zone. The interconnected nature of tectonic processes means that disturbances in one region can influence geological activity across entire plate boundaries, oceanic currents, those massive conveyor belts that transport heat and dissolved gases between ocean basins and regulate global climate patterns, experience disruption as tsunami waves interfere with the density-driven circulation that has operated for millions of years. The thermohaline circulation that carries warm surface water, poleward, while returning cold deep water toward the equator, depends on precise temperature and salinity gradients that could be altered by the mixing and displacement associated with impact-generated waves. These circulation changes might persist for years, influencing weather patterns and marine ecosystems across the globe. Marine ecosystems throughout the Pacific face unprecedented disruption as tsunami waves transport deep ocean water to surface layers while driving surface organisms to crushing depths where sunlight cannot penetrate. Phytoplankton communities that form the base of oceanic food webs depend on stable water column structure to maintain their position in the photic zone where photosynthesis remains possible. The violent mixing associated with tsunami passage could redistribute these microscopic organisms in ways that cascade through the entire marine food web, effects that might persist for decades as ecosystem structure slowly recovers. The irony spreads across oceanic scales. The Pacific, named for its perceived tranquility by Magellan's expedition, and long considered a barrier that isolated human civilizations, now becomes the stage for the most violent collision between terrestrial and extraterrestrial matter in recorded history. The ocean that has absorbed countless smaller impacts from meteoroids and space debris over geological time now faces energy inputs that exceed its capacity for gradual dissipation through normal wave action and tidal circulation. Hydrothermal vent communities clustered around mid-ocean ridges where tectonic plates separate and expose the Earth's interior to direct contact with seawater may find their delicate chemical equilibria disrupted by the pressure waves and water displacement associated with major impact events. These ecosystems, based on chemosynthetic bacteria that derive energy from hydrogen sulfide and other reduced compounds, represent some of Earth's most extreme environments and possibly the closest analogues to early life that emerged in similar conditions billions of years ago. The impact's effects on these communities could provide insights into life's resilience under conditions that prevailed during the late heavy bombardment. Tsunami wave heights in deep ocean water remain deceptively modest, typically less than 1 meter, even for the most energetic events. But this belies the enormous energy content distributed across wavelengths measured in hundreds of kilometers. As these waves approach continental shelves and encounter shallower water, shoaling effects concentrate their energy into increasingly smaller volumes, amplifying wave heights by factors that can exceed 100. Coastal regions face waves that may reach heights measured in tens of meters, moving inland with velocities that strip away centuries of human development and geological sediment accumulation. The Pacific Plate, largest tectonic structure on Earth's surface and moving northwest at a rate of several centimeters per year, experiences instantaneous stress loading as impact energy couples into crustal rock through direct mechanical contact and seismic wave propagation. This sudden loading, equivalent to millions of years of normal tectonic stress applied in seconds, may trigger fault motion along transform boundaries and subduction zones that have remained locked for centuries. The mechanical coupling between impact energy and tectonic processes represents one of the least understood aspects of large impact events. Atmospheric pressure waves generated by the impact create air-coupled waves that propagate through the atmosphere at acoustic velocities. Pressure disturbances that can arrive at distant locations before the faster-moving tsunami waves travelling through ocean water. These atmospheric waves, though much weaker than the waterborne tsunamis, can still generate dangerous oscillations in enclosed bodies of water thousands of kilometers from the impact site. Lakes, reservoirs, and harbours may experience siege motion triggered by atmospheric pressure variations that create standing wave patterns, potentially destructive to coastal infrastructure. Ocean chemistry faces alteration through the injection of vaporized comet material into seawater, exotic isotopes and molecular compounds that have never participated in terrestrial biogeochemical cycles. The impact vaporizes not only the comet fragments, but also substantial volumes of seawater, creating a vapor plume that rises through the atmosphere before condensing and returning to the ocean surface as precipitation enriched with interstellar chemistry. These chemical modifications, though representing tiny fractions of total oceanic composition, could be detected in marine sediments and ice cores for millions of years as geochemical evidence of the impact event. Abyssal plains, those vast underwater deserts covered by fine sediments that have accumulated for millions of years in the deep ocean basins, face immediate disruption as impact-generated currents redistribute sediment layers that preserve Earth's climate history. Turbidity currents triggered by seafloor shaking transport sediments from continental margins into the deep ocean, creating chaotic deposits that interrupt the normally regular accumulation of microscopic marine organisms. Future paleoclimatologists studying sediment cores will encounter a distinct boundary layer marking this moment when interstellar material violently entered Earth's oceanic system. Only took the Pacific Basin 150 million years to reach its current configuration through the processes of seafloor spreading and plate tectonics. And now this ancient oceanic realm faces energy inputs that compress geological timescales into moments of catastrophic change as fragments of another star system deliver their accumulated kinetic energy into the water that covers most of Earth's surface. Continental shelves around the Pacific Basin begin to register the first seismic tremors as compressional waves generated by oceanic impact propagate through Earth's crust at velocities exceeding 8 kilometers per second. faster than the tsunami waves racing across the ocean surface toward distant coastlines. These P waves, travelling through solid rock with the mathematical precision of elastic wave theory, arrive at seismic monitoring stations from California to Japan within minutes of impact, their distinctive signatures revealing both the magnitude and location of energy release. The continental margins, those submerged edges of ancient landmasses where thick sedimentary deposits record millions of years of erosion and deposition, now transmit the mechanical shock of interstellar collision through crystalline basement rocks that formed billions of years ago. Fault systems that have accumulated tectonic stress for decades suddenly face additional loading as impact-generated seismic energy propagates through crustal structures already near their failure threshold. The San Andreas Fault System, marking the boundary between Pacific and North American plates where lateral motion proceeds at several centimeters per year, experiences instantaneous stress changes that could trigger the release of centuries of accumulated strain energy. These fault networks, mapped through decades of geological investigation and earthquake monitoring, now serve as conduits that amplify and redirect the seismic energy from a single oceanic impact across entire continental regions. The Cascadia subduction zone, where the Juan de Fuca plate descends beneath North America and creates the conditions for both explosive volcanism and great earthquakes, responds to the seismic trigger with mechanical inevitability. This convergent margin, locked by friction along a fault surface that extends from surface to depths exceeding 50 kilometers, has historically generated magnitude 9 earthquakes that reshape coastlines and trigger tsunamis throughout the Pacific Basin. The additional stress imposed by impact-generated seismic waves may provide the final increment needed to overcome frictional resistance and initiate fault rupture along hundreds of kilometers of plate boundary. Scientists puzzle over the complex interactions between natural tectonic processes and the artificial loading imposed by extraterrestrial impact. Stress transfer mechanisms that operate through both direct mechanical coupling and dynamic triggering by seismic waves. Earthquake prediction, already challenging due to the nonlinear nature of fault system mechanics, becomes essentially impossible when external forcing functions introduce energy inputs far exceeding normal tectonic rates. Computer models struggle to incorporate both the impulsive nature of impact loading and the heterogeneous stress conditions that characterize real fault networks. Mount Rainier, one of the most dangerous volcanoes in the Cascade Range due to its proximity to major population centers and its history of debris flows that have reached Puget Sound, sits atop a magma chamber that contains molten rock under pressures determined by the weight of overlying solid rock. Seismic waves passing through this volcanic system could alter the stress conditions that maintain magma in liquid form, potentially triggering explosive eruptions through mechanisms similar to those that cause champagne bottles to overflow when shaken. The interconnected nature of volcanic systems means that disturbances at one location can influence magmatic processes across entire volcanic arcs. Sedimentary basins filled with millions of years of accumulated rock debris amplify seismic waves through resonance effects that concentrate energy at specific frequencies determined by basin geometry and the elastic properties of different rock layers. The Los Angeles Basin, filled with sediments eroded from surrounding mountain ranges and underlain by complex fault networks, creates ideal conditions for seismic amplification that can increase ground motion by factors of 10 or more compared to solid bedrock. These amplification effects, well documented during historical earthquakes, now face input signals with frequency content unlike any previously recorded. The Ring of Fire, that belt of volcanic activity surrounding the Pacific Basin, where subducting oceanic plates create the conditions for explosive magmatism, extends from the Aleutian Islands through Japan, Indonesia, and the Western Americas in a nearly continuous chain of active volcanoes. This volcanic arc, representing the surface expression of mantle convection and plate tectonic processes, contains hundreds of potentially active volcanoes whose magma chambers exist in delicate equilibrium between solid and liquid phases. The seismic energy propagating through this system could trigger simultaneous eruptions across multiple volcanic centers, creating a cascade of atmospheric and climatic effects, transform faults, where tectonic plates slide past each other horizontally rather than converging or diverging, create zones of intense mechanical coupling that efficiently transmit seismic energy across great distances. The Alpine Fault System in New Zealand, capable of generating magnitude 8 earthquakes that rupture across hundreds of kilometers of South Island topography, faces stress loading from seismic waves that have traveled halfway around the globe. The mechanical properties of crustal rock ensure that impact energy dissipated in the Pacific Ocean can influence geological processes on continents thousands of kilometers away. The irony propagates through solid rock continental shelves and fault systems that formed through millions of years of gradual tectonic motion, now experience instantaneous stress changes equivalent to centuries of normal geological activity, compressed into seconds of seismic wave passage. The patient accumulation of strain energy that characterizes earthquake cycles faces disruption by forces originating not from Earth's interior, but from the kinetic energy of matter that formed in orbit around another star. Groundwater systems within sedimentary basins experience liquefaction, as seismic shaking reduces the effective stress that maintains soil structure, transforming solid ground into fluid-like conditions that cannot support the weight of buildings and infrastructure. This process, well documented during major earthquakes, depends on specific combinations of soil type, water content, and shaking intensity that create conditions where granular materials lose their internal friction and behave like viscous fluids. The widespread liquefaction triggered by impact-generated seismic waves could affect regions far from any natural earthquake sources. Landslide susceptibility increases dramatically as seismic shaking destabilizes slopes that have maintained their equilibrium for thousands of years under the influence of gravity, weathering, and gradual erosion. Steep terrain throughout the Pacific Basin margins, already rendered unstable by tectonic uplift and stream cutting, faces dynamic loading that exceeds the threshold for slope failure across vast areas simultaneously. These mass-wasting events, triggered by seismic energy but controlled by local topography and rock strength, could continue for years as destabilized slopes gradually adjust to new equilibrium configurations. Coastal uplift and subsidence, normally occurring over thousands of years as tectonic processes gradually deform Earth's surface, may take place instantaneously as fault rupture redistributes crustal stress and alters the elevation of vast coastal regions. Earthquake-induced land level changes, documented during historical great earthquakes, typically measure in meters over areas spanning hundreds of kilometers. The magnitude of stress redistribution associated with impact-triggered fault rupture could permanently alter coastline configurations and tidal patterns throughout the Pacific Basin. Seismic wave attenuation, the gradual loss of energy as elastic waves propagate through imperfectly elastic crustal rock, normally ensures that earthquake effects diminish with distance from their source. However, the enormous energy release associated with major impact events creates seismic signals strong enough to remain above background noise levels even after traveling through thousands of kilometers of solid rock. Global seismic networks detect these signals as they circumnavigate the planet multiple times. Interference patterns that encode information about both the source mechanism and Earth's internal structure, mountain building processes, operating over millions of years as tectonic forces compress and uplift crustal rocks into linear ranges that mark ancient collision zones between lithospheric plates, face instantaneous modification as seismic energy propagates through existing orogenic belts. The mechanical coupling between seismic waves and mountain root systems, those deep crustal structures that provide isostatic support for high topography, could trigger rapid adjustments in surface elevation that normally require geological time to accomplish. Underground mining operations throughout the Pacific Rim, from copper mines in Chile to coal mines in Australia, experience seismic loading that far exceeds the design criteria for underground excavations. These artificial caves, maintained against the lithostatic pressure of overlying rock through support systems designed for normal seismic conditions, face dynamic stresses that could trigger widespread collapse of underground workings. The mining-induced seismicity that normally poses localized hazards becomes insignificant compared to the regional seismic environment created by impact energy propagation, petroleum reservoirs, those subsurface accumulations of hydrocarbons trapped by specific geological configurations of permeable and impermeable rock layers, experience pressure changes as seismic waves alter the stress conditions that maintain fluid flow patterns. Enhanced oil recovery through seismic stimulation, already used industrially to increase production rates, occurs naturally as impact-generated seismic energy propagates through hydrocarbon-bearing formations. These pressure pulses could trigger changes in reservoir behavior that affect petroleum production for decades. Only took Earth's continental margins 2 billion years to accumulate their current thickness of sedimentary rock through erosion, transportation, and deposition processes driven by plate tectonics and surface weathering. And now these passive margins face seismic energy inputs that compress normal geological processes into moments of crustal deformation as the mechanical shock of interstellar collision propagates through rock formations that preserve the history of continental evolution. The atmosphere's chemical composition, stable for millions of years through the delicate balance between biological production and consumption of gases, faces unprecedented disruption as vaporized comet material mixes with terrestrial air in proportions that challenge every atmospheric chemistry model. Water vapor bearing deuterium ratios characteristic of interstellar ice clouds rises through the troposphere, while exotic nitrogen compounds synthesized in the radiation environment of another stellar system begin to participate in ozone chemistry through reaction pathways that have never operated in Earth's atmosphere. The chemical equilibrium that has maintained breathable air for complex life now encounters molecular species whose isotopic signatures encode the nuclear processes that occurred in stars that died before our sun ignited. Ozone depletion proceeds through catalytic cycles involving chlorine and nitrogen compounds. But the exotic chemistry injected by the comet's atmospheric destruction introduces reaction pathways that atmospheric chemists have never considered. Nitric oxide, bearing the isotopic signature of cosmic ray bombardment during interstellar transit, participates in ozone destruction with reaction rates that differ subtly from terrestrial nitrogen chemistry due to quantum mechanical effects associated with nuclear mass differences. These isotope effects, normally negligible in atmospheric processes, become significant when processing rates exceed the atmosphere's capacity for chemical buffering. Stratospheric heating from infrared radiation emitted by the glowing debris cloud alters reaction rates throughout the ozone layer, accelerating photochemical processes that normally proceed at rates controlled by solar ultraviolet intensity and seasonal temperature variations. The sudden temperature increase, measured in tens of degrees across vast regions of the stratosphere, shifts chemical equilibria in ways that could reduce ozone concentrations for months or years as the excess thermal energy slowly radiates to space. This heating occurs at altitudes where ozone reaches its maximum concentration, precisely the region most critical for shielding Earth's surface from harmful ultraviolet radiation. Aerosol particles created by the condensation of vaporized comet material in the cooling upper atmosphere provide nucleation sites for chemical reactions that normally occur only in the gas phase or on the surfaces of natural atmospheric particles. These exotic aerosols, composed of refractory materials that formed around another star, have surface properties unlike any terrestrial atmospheric constituents. Their catalytic effects on atmospheric chemistry could persist for years as the particles gradually settle through the atmosphere under the influence of gravity and atmospheric circulation. Scientists puzzle over the long-term atmospheric effects of injecting interstellar organic compounds into Earth's oxidizing atmosphere, complex carbon molecules that have never participated in terrestrial biogeochemical cycles. polycyclic aromatic hydrocarbons synthesized in the outflow from red giant stars now face oxidation by atmospheric hydroxyl radicals, creating reaction products whose environmental effects remain completely unknown. The atmospheric chemistry of these exotic organic compounds could produce greenhouse gases or ozone-depleting substances whose impacts might not become apparent for decades. Greenhouse gas concentrations face temporary but significant alteration, as water vapor and carbon dioxide released from the comet's vaporization add to the atmospheric inventory of infrared active molecules. The additional water vapor, injected directly into the stratosphere where it normally exists in only trace concentrations, could enhance the greenhouse effect for months as it gradually redistributes through atmospheric circulation. Carbon dioxide, bearing unusual isotopic ratios, provides atmospheric scientists with traces that will remain detectable in ice cores and tree rings for centuries as evidence of this extraterrestrial input. Atmospheric circulation patterns, driven by temperature gradients between equatorial and polar regions, experience disruption as the heating associated with comet vaporization creates thermal anomalies that persist for months. The jet streams that govern weather patterns in both hemispheres could shift latitude or intensity as the altered temperature structure changes the atmospheric pressure gradients that drive these high-altitude wind systems. These circulation changes might trigger unusual weather patterns globally, as the atmosphere slowly readjusts to its new thermal equilibrium. Cloud formation mechanisms face alteration, as exotic aerosol particles change the nucleation processes that control precipitation patterns worldwide. The comet-derived particles, with surface chemistries unlike terrestrial dust or sea salt, could enhance or suppress cloud formation depending on their hygroscopic properties and ice nucleation efficiency. Changes in cloud cover and precipitation patterns could persist for years as these particles gradually remove from the atmosphere through wet and dry deposition processes. The irony unfolds across atmospheric layers. The same oxidizing atmosphere that has supported complex life for billions of years through photosynthetic oxygen production now serves as a chemical reactor that processes exotic materials from another stellar system, potentially altering its own composition through reactions with alien chemistry. The atmospheric envelope that has remained in chemical equilibrium through biological feedback mechanisms faces perturbations that exceed the buffering capacity of natural biogeochemical cycles. Atmospheric escape processes, normally limited to light hydrogen atoms that can reach escape velocity in the hot upper atmosphere, experience enhancement as the energy deposited by comet vaporization heats atmospheric gases to temperatures where heavier molecules can achieve the velocities needed to escape Earth's gravitational attraction. This atmospheric loss, normally negligible over human timescales, could become measurable as exotic heating rates accelerate the thermal escape of water vapor and other atmospheric constituents. Ionospheric chemistry faces disruption as the plasma created by comet vaporization increases electron densities far above normal levels, altering the photochemical balance that maintains the conducting layers essential for radio communication. The enhanced ionization could persist for months as exotic atoms and molecules continue to absorb solar radiation more efficiently than normal atmospheric constituents. Radio propagation conditions might remain anomalous long after the visible effects of the impact have faded from observation. Atmospheric isotope ratios, normally used as traces for understanding source and sink processes in biogeochemical cycles, acquire new signatures that reflect the nuclear processes operating in the comet's birth stellar system. Carbon-13 to carbon-12 ratios in atmospheric carbon dioxide, oxygen-18 variations in water vapor, and noble gas isotopic compositions all carry information about stellar nucleosynthesis that occurred light-years from Earth. These isotopic anomalies will remain detectable in atmospheric measurements for decades as evidence of extraterrestrial material input. Photochemical smog formation in urban areas could experience enhancement or suppression as exotic organic compounds participate in the complex reaction networks that create ground-level ozone and particulate matter. The alien chemistry injected into the atmosphere includes molecular precursors that have never been evaluated for their role in tropospheric ozone formation, potentially creating air quality problems in populated regions through reaction pathways not anticipated by current atmospheric chemistry models. Atmospheric lifetime calculations for greenhouse gases and ozone-depleting substances rely on reaction rate constants measured under laboratory conditions using terrestrial atmospheric constituents. The exotic chemistry introduced by comet vaporization could alter these lifetimes through previously unknown reaction pathways, potentially extending or shortening the atmospheric residence times of climatically important trace gases. These changes in atmospheric chemistry could influence climate and ozone recovery rates for decades. Biogeochemical feedback mechanisms that normally maintain atmospheric composition through the activities of marine and terrestrial ecosystems face disruption as exotic chemical inputs alter the nutrient cycles that control biological productivity. Marine phytoplankton, responsible for producing much of atmospheric oxygen, could experience toxicity from heavy metals and organic compounds that never existed in terrestrial environments. The biological response to exotic atmospheric chemistry represents one of the least predictable long-term consequences of major impact events. Atmospheric pressure fluctuations generated by the explosive vaporization of comet material create acoustic waves that propagate globally through the atmosphere, infrasonic signals that can trigger avalanches and landslides in mountainous terrain thousands of kilometers from the impact site. These pressure waves, traveling at the speed of sound through atmospheric layers with different temperatures and densities, create complex interference patterns that focus acoustic energy in specific geographic regions through atmospheric focusing effects. Stratospheric ozone recovery, already challenged by the legacy of industrial chlorofluorocarbon emissions, faces additional complications from exotic halogens released during comet vaporization. Chlorine and bromine compounds synthesized through cosmic ray interactions during the comet's interstellar journey could contribute to ozone destruction through catalytic cycles that operate more efficiently than the industrial chemicals that created the Antarctic ozone hole. The stratospheric chemistry of these extraterrestrial halogens could delay ozone layer recovery by decades. Only took Earth's atmosphere 4 billion years to evolve from a reducing environment dominated by hydrogen and methane to the oxygen-rich mixture that sustains aerobic life. And now this chemically complex envelope faces molecular inputs that encode the stellar nucleosynthesis history of distant galactic regions. Exotic chemistry that challenges the atmospheric equilibrium maintained through eons of biological evolution and geochemical cycling. The biosphere, that thin shell of life extending from ocean depths to atmospheric heights, where 4 billion years of evolution have created interconnected webs of organisms adapted to Earth's specific chemical and physical conditions, now confronts an evolutionary bottleneck unlike any in recorded biological history. Ecosystems from tropical rainforests to Arctic tundra face simultaneous pressures that compress normal evolutionary timescales into ecological moments, forcing rapid adaptation or extinction as atmospheric chemistry, climate patterns, and radiation environments shift beyond the tolerance ranges that have defined habitable conditions since complex life emerged from the primordial seas. Marine food webs, anchored by phytoplankton communities that convert dissolved carbon dioxide into organic matter through photosynthesis, experience disruption as altered atmospheric chemistry changes ocean surface conditions and exotic trace metals from the vaporized comet enter marine biogeochemical cycles. These microscopic organisms, responsible for producing approximately half of Earth's atmospheric oxygen, prove sensitive to subtle changes in nutrient ratios, pH levels, and trace element concentrations that now include isotopic signatures from another stellar system. Primary productivity shifts could cascade through entire ocean ecosystems as the chemical foundation of marine life adjusts to unprecedented inputs. Forest ecosystems worldwide face atmospheric conditions outside the environmental parameters that have governed plant evolution for hundreds of millions of years. Altered radiation spectra as stratospheric ozone depletion allows increased ultraviolet penetration to Earth's surface and chemical inputs that include organic compounds never before encountered by terrestrial biochemistry. Trees, with lifespans measured in centuries, cannot adapt genetically to rapid environmental changes and must rely on physiological tolerance ranges evolved for pre-impact atmospheric conditions. The mismatch between evolutionary adaptation timescales and environmental change rates creates selection pressures comparable to those that drove mass extinction events in Earth's geological past. Atmospheric microorganisms, those aerial communities of bacteria and archaea that drift through the troposphere and participate in cloud formation and atmospheric chemistry, encounter exotic organic compounds that could serve either as novel energy sources or as toxic contaminants depending on their biochemical properties. These microorganisms, adapted to metabolize terrestrial atmospheric constituents, now face molecular species synthesized under the radiation conditions of interstellar space. The atmospheric microbiome could undergo rapid evolutionary changes as natural selection operates on generation times measured in hours rather than years. Scientists puzzle over the long-term biological effects of exposing Earth's biosphere to isotopic compositions characteristic of different stellar nucleosynthesis environments, chemical elements with neutron-to-proton ratios that have never participated in terrestrial biochemistry. Heavy isotopes of carbon, nitrogen, and sulfur now entering food webs could alter enzyme kinetics and metabolic pathways through subtle quantum mechanical effects that influence reaction rates and molecular binding energies. These isotope effects, negligible in most chemical processes, become significant in biological systems where precise molecular recognition determines cellular function. Pollinating insects, already under stress from habitat loss and pesticide exposure, face additional challenges as altered atmospheric chemistry affects both plant flowering patterns and insect navigation systems. Bees and other pollinators rely on ultraviolet light patterns invisible to human eyes for flower recognition and navigation, systems that could be disrupted by changes in atmospheric opacity and spectral transmission. The collapse of pollination networks could trigger cascading effects through terrestrial ecosystems as plant reproduction rates decline and food webs dependent on flowering plants face disruption. Coral reef ecosystems, those tropical marine communities that support approximately 25% of ocean species, despite occupying less than 1% of marine habitat, experience multiple simultaneous stresses as ocean chemistry changes combine with atmospheric effects to create conditions outside their narrow tolerance ranges. Coral bleaching, the breakdown of symbiotic relationships between coral animals and photosynthetic algae, could occur globally as temperature increases and chemical changes exceed the adaptive capacity of these ancient partnerships that have persisted for millions of years. Soil microbial communities, the invisible ecosystems that drive nutrient cycling and support all terrestrial plant life, encounter exotic organic compounds and altered precipitation chemistry as atmospheric deposition carries the chemical signatures of interstellar space to Earth's surface. These microbial networks, evolved over billions of years to process terrestrial organic matter, may lack the enzymatic pathways needed to metabolize alien chemistry. Soil ecosystem collapse could disrupt nutrient cycles and agricultural productivity for decades, as microbial communities slowly adapt to new chemical environments. The irony spreads through ecological networks. Life on Earth, evolved under the protective envelope of a stable atmosphere and magnetic field, now faces selection pressures from materials that formed under the influence of a different star. Cosmic chemistry that challenges the biochemical assumptions underlying 4 billion years of terrestrial evolution. The same processes that drove the emergence of complex life through natural selection now operate under environmental conditions that have no precedent in Earth's biological history. Agricultural systems, dependent on carefully selected crop varieties optimized for specific climate and soil conditions, face simultaneous challenges from altered growing seasons, change precipitation patterns, and soil chemistry modifications that could reduce yields precisely when human populations require maximum food security. Crop plants, genetically uniform within varieties and lacking the genetic diversity that enables wild populations to respond to environmental change, prove particularly vulnerable to rapid shifts in growing conditions. Global food security could face threats comparable to those created by major volcanic eruptions that have triggered famines throughout human history. Migratory animal populations, guided by magnetic navigation systems evolved to use Earth's stable geomagnetic field, may experience disruption as electromagnetic effects associated with the impact alter local magnetic field patterns. Birds, marine mammals, and other species that rely on magnetic compass orientation for long-distance navigation could become disoriented during critical migration periods. The timing mismatch between altered environmental cues and evolutionary programming could affect reproduction success and survival rates across entire species ranges. Arctic ecosystems, already experiencing rapid change due to climate warming, face accelerated transformation as altered atmospheric circulation patterns and increased energy input accelerate ice loss and permafrost thawing. Species adapted to stable ice conditions, from polar bears to ice-dependent seals, confront habitat changes that occur faster than ecological adaptation can occur. The Arctic Ocean, potentially ice-free for the first time in millions of years, would undergo complete ecosystem reorganization as marine communities shift from ice-adapted to open water configurations. Freshwater ecosystems, from mountain lakes to major river systems, experience chemical changes as atmospheric deposition introduces exotic trace elements, and altered precipitation patterns modify hydrological cycles that have operated consistently for thousands of years. Aquatic organisms, particularly sensitive to water chemistry changes, face conditions that exceed the tolerance ranges evolved for natural water compositions. Fish populations, already stressed by habitat modification and pollution, could experience additional mortality from trace metal, toxicity and pH changes associated with atmospheric chemistry modifications. Deep ocean ecosystems, those abyssal communities that depend on the slow rain of organic matter from surface waters, may experience disruption as changes in surface productivity alter the quantity and quality of nutrients reaching the seafloor. Organisms adapted to food-limited deep-sea conditions could face either starvation or toxicity as exotic organic compounds settle through the water column. These deep communities, with generation times measured in decades, cannot respond rapidly to environmental changes and may experience local extinctions that persist for centuries. Genetic bottlenecks, those population contractions that reduce species diversity and evolutionary potential, could affect numerous species simultaneously as environmental changes exceed the tolerance ranges of individuals with specific genetic combinations. The loss of genetic diversity during extinction bottlenecks reduces the evolutionary potential of surviving populations, making them more vulnerable to future environmental changes. Recovery of genetic diversity requires thousands of generations, timescales that exceed human planning horizons for conservation management. Keystone species, those organisms whose ecological effects far exceed their biomass or abundance, could experience disproportionate impacts that cascade through entire ecosystems as environmental changes affect critical life history stages or behavioral patterns. The collapse of keystone species populations triggers non-linear ecological responses that can reorganize entire biological communities. Ecosystem recovery from keystone species loss typically requires decades to centuries as new species assemblages develop and stabilize. Evolutionary rescue, the process by which natural selection enables populations to adapt genetically to environmental change, faces severe time constraints as the rate of environmental modification exceeds the generation times needed for adaptive mutations to spread through populations. Large-bodied species with long generation times prove particularly vulnerable to rapid environmental change, while small organisms with short generation times may evolve quickly enough to track changing conditions. The differential survival of species with different life history strategies could fundamentally alter the composition of Earth's biological communities. only took the biosphere 4 billion years to evolve from simple prokaryotic cells to the complex ecosystems that now support millions of species across every habitat on Earth. And now this vast biological network faces environmental pressures that compress evolutionary time into ecological moments, as life confronts chemistry from another star system through selection mechanisms that have shaped terrestrial evolution since the first organic molecules learned to reproduce themselves in the primordial ocean. Geological time begins its patient work of healing as Earth's crustal processes, operating with the inexorable persistence that has resurfaced the planet countless times across 4.5 billion years, start to absorb and redistribute the energy of interstellar collision through mechanisms that will outlast human civilization by millions of years. Erosion and weathering, those chemical and physical processes that have carved mountains into sand and transported continents grain by grain to oceanic depths, now face the task of processing impact debris whose exotic isotopic signatures will remain detectable in sedimentary rocks, long after the last traces of human activity have vanished from the geological record. Tectonic processes, driven by the slow convection of Earth's mantle and the gradual cooling of the planet's molten interior, begin to incorporate the mechanical effects of impact-induced seismic energy into the ongoing cycle of crustal creation and destruction. New fault scarps created by earthquake rupture will undergo millions of years of gradual modification, as weathering rounds their sharp edges and stream erosion cuts valleys that will eventually become major river systems. The sudden vertical displacements that altered coastlines and mountain profiles in moments will slowly equilibrate through isostatic adjustment as the underlying mantle responds to changed surface loads. Sedimentary deposition accelerates temporarily as mass-wasting events triggered by seismic shaking deliver unusual quantities of rock debris to river systems and ocean basins, creating distinctive stratigraphic layers that will mark this moment in Earth's geological timeline for as long as these rocks survive the cycling of crustal material through subduction zones and mountain-building episodes. The impact-generated debris flows and landslides deposit angular rock fragments in patterns unlike normal sedimentary processes, creating breccia layers that future geologists, if any exist, will recognize as evidence of catastrophic disruption. Impact craters, those circular scars that mark violent encounters between planetary surfaces and cosmic projectiles, begin their transformation from sharp-rimmed excavations to subdued topographic features through the action of wind, water, and gravity operating across millions of years. The largest craters created by comet fragments may persist as recognizable features for tens of millions of years, gradually filled by sediment accumulation, while their raised rims undergo erosion that will eventually reduce them to subtle circular patterns visible only through careful topographic analysis. Scientists puzzle over the long-term preservation potential of exotic materials embedded in impact deposits, isotopic signatures that could remain detectable in terrestrial rocks for billions of years as chemical evidence of extraterrestrial input. The platinum group elements and rare earth metals concentrated in the comet's nucleus will be dispersed globally through atmospheric transport and incorporated into sedimentary layers at concentrations far exceeding normal crustal abundances. These chemical anomalies will serve as time markers comparable to the iridium layer that marks the Cretaceous-Paleogene boundary and the extinction of non-avian dinosaurs. Hydrothermal systems, those networks of hot water circulation that form where groundwater encounters elevated temperatures from buried heat sources, develop new configurations as impact-related fracturing creates enhanced permeability in crustal rocks. These hydrothermal networks, operating over thousands of years, will gradually leach and redistribute the exotic trace elements introduced by comet vaporization, concentrating some metals into potential ore deposits, while dispersing others so thoroughly that their extraterrestrial origin becomes undetectable except through sophisticated geochemical analysis. Magnetic field variations recorded in igneous rocks cooling from magma heated by impact processes will preserve directional information about Earth's magnetic field configuration at the moment of impact. creating paleomagnetic records that encode both the intensity and orientation of the geomagnetic field during this extraordinary geological event. These magnetic signatures, locked into iron-bearing minerals as they cool below their Curie temperature, will remain stable for hundreds of millions of years unless subsequent heating or deformation resets their magnetic memory. Volcanic activity triggered by impact-induced seismic energy follows its own timeline as magma chambers pressurized by earthquake-generated stress changes gradually cool and crystallize over thousands of years. The igneous rocks formed from this volcanism will carry chemical signatures reflecting both normal mantle compositions and the exotic trace elements introduced by atmospheric deposition of vaporized comet material. Future petrologists studying these rocks will find isotopic anomalies that reveal the extraterrestrial contribution to what otherwise appears to be normal volcanic activity. The irony unfolds across geological timescales Earth's surface, constantly renewed by tectonic processes that erase most evidence of past events within hundreds of millions of years, will preserve chemical traces of this interstellar visitor longer than any mountain range or ocean basin currently existing on the planet's surface. The exotic isotopes dispersed by impact processes become incorporated into the crustal inventory of trace elements, permanent additions to Earth's chemical composition that will survive through multiple cycles of continental drift and oceanic spreading. Soil formation processes, operating at rates measured in centimeters per millennium, begin to incorporate exotic trace elements into developing soil profiles as atmospheric deposition and weathering of impact debris introduce chemical components never before available to terrestrial pedogenesis. These soils, forming from the physical and chemical breakdown of impact-modified bedrock, will develop trace element signatures that remain detectable for millions of years as evidence of extraterrestrial input into near-surface geochemical cycles. Groundwater systems slowly equilibrate with new chemical compositions as exotic materials dissolved from impact debris migrate through aquifer systems at rates controlled by hydraulic conductivity and geochemical reaction kinetics. The movement of these chemical traces through subsurface environments follows flow paths that may require thousands of years to reach discharge points, creating long-term contamination or enrichment plumes whose exotic isotopic signatures will puzzle future hydrogeologists. River systems adjust their profiles and channel configurations to accommodate the enormous sediment loads delivered by impact-triggered mass wasting, a process that will require centuries to millennia as stream networks gradually transport the excess debris to depositional environments in floodplains, deltas, and submarine fans. The exotic trace element signatures carried by this sediment will be preserved in these depositional systems as chemical evidence of the impact event. Oceanic sediment accumulation incorporates the chemical fingerprints of vaporized comet material into deep-sea deposits that will remain undisturbed for millions of years in abyssal environments where bioturbation rates are minimal and sedimentation proceeds at steady rates measured in millimeters per 1,000 years. These marine sediments will preserve high-resolution records of the atmospheric and oceanic responses to impact, including the temporal evolution of exotic trace element deposition as the atmosphere slowly processed and removed impact-generated aerosols. Glacial ice, where it exists in polar regions and high-altitude environments, begins to incorporate atmospheric dust and chemical signatures from impact processes into annual accumulation layers that will preserve detailed records of atmospheric composition changes for thousands of years, until the ice eventually flows to ablation zones or calves into the ocean. These glacial archives will provide future climate scientists with precise temporal records of how Earth's atmosphere responded to the injection of exotic materials. Limestone formation in marine environments incorporates trace amounts of exotic strontium and other elements into calcium carbonate structures as marine organisms continue their normal shell-building activities using seawater, whose chemistry has been subtly altered by the dissolution of impact debris. These biogenic carbonates will preserve isotopic records of ocean chemistry changes that persist for as long as the limestone formations survive, weathering and metamorphism. Metamorphic processes, operating where impact-generated heat and pressure create conditions that alter existing rock compositions and structures, produce new mineral assemblages that incorporate exotic trace elements into crystal lattices designed to accommodate specific chemical compositions. These metamorphic rocks will preserve evidence of the extreme conditions created by impact processes, while incorporating extraterrestrial chemical signatures into stable mineral phases that can survive for billions of years. Coal formation, from vegetation that grew in soils enriched with exotic trace elements, will create organic sedimentary deposits whose trace element chemistry reflects the atmospheric deposition of vaporized comet material onto terrestrial ecosystems. These coal deposits, if they survive long enough to form, will provide geochemists with records of how exotic materials entered terrestrial biogeochemical cycles through plant uptake and organic matter accumulation, or deposit formation through hydrothermal concentration of exotic platinum group elements, and rare earth metals could create economically significant mineral deposits as groundwater circulation systems slowly leach and concentrate these materials in favorable geological environments. The formation of these ore bodies will require thousands to millions of years as hydrothermal processes gradually concentrate dispersed exotic elements into miniable accumulations. Only took Earth 4.5 billion years to develop the complex geological processes that continuously resurface the planet through plate tectonics, erosion, and sedimentation. And now these ancient mechanisms begin their patient work of incorporating the chemical signatures of another stellar system into the rock record that preserves Earth's history, ensuring that traces of interstellar matter will remain detectable in terrestrial geology long after all other evidence of this cosmic collision has been erased by the relentless cycling of crustal material through the engines of geological time. Deep time absorbs the violence of cosmic collision with the indifference of geological process, reducing the catastrophic energy release that reshaped continents and extinguished species to merely another brief entry in the 4.5 billion year chronicle that Earth's rocks preserve in their crystalline structures and sedimentary layers. The impact event, overwhelming in its immediate effects on human timescales, represents less than a microsecond in the vast span of planetary evolution, a momentary perturbation in the slow dance of crustal recycling, an atmospheric evolution that has operated since the Hadean Eon, when our world first solidified from the disk of debris surrounding the young sun. Rock layers accumulate grain by grain above the distinctive chemical signature that marks this moment, sedimentary deposits that will eventually reach thicknesses measured in kilometers as millions of years of erosion and deposition gradually bury the impact horizon beneath the weight of accumulated geological time. Future stratigraphers, if any exist to study Earth's rocks in the distant future, will recognize this boundary through its anomalous concentrations of platinum group elements and isotopic ratios that encode the nuclear processes of stellar nucleosynthesis that occurred in distant galactic regions billions of years before our solar system formed. The exotic isotopes dispersed globally by impact processes begin their integration into Earth's biogeochemical cycles. Trace amounts of heavy elements that will circulate through atmosphere, hydrosphere, and biosphere for millions of years before eventually being subducted into the mantle through plate tectonic processes or locked permanently into stable mineral phases in continental crust. These chemical traces, invisible except to the most sensitive analytical instruments, will remain detectable in terrestrial materials for time spans that dwarf the entire history of complex life on Earth. Continental drift continues its patient rearrangement of crustal geography, moving the impact sites and their associated geological features across Earth's surface at rates measured in centimeters per year, velocities that will transport evidence of interstellar collision to entirely different climate zones and depositional environments over the tens of millions of years required for significant continental motion. The impact craters and seismic disruption patterns created in moments will be carried by plate motion across thousands of kilometers, their original geographic context gradually obscured by the ongoing reorganization of Earth's surface geography. Scientists working millions of years in the future should intelligent life persist to undertake such investigations, will puzzle over the geochemical anomalies preserved in rocks formed during this epoch, isotopic signatures that clearly indicate extraterrestrial input, but whose source remains mysterious due to the obliteration of most impact evidence by subsequent geological processes. The exotic chemistry will be unmistakable, but the specific mechanism of its introduction into Earth systems may become as debated among future geologists as the cause of mass extinction. Events remains among contemporary researchers. Stellar evolution ensures that the Sun will continue its steady brightening for billions of years, as hydrogen fusion in the solar core gradually increases luminosity and alters the energy balance that drives Earth's climate systems. Changes that will eventually render the planet uninhabitable regardless of any other factors. The impact event, catastrophic in its immediate effects, represents merely one episode in the much longer story of planetary evolution that will ultimately be controlled by astronomical processes operating on timescales that reduce geological events to brief interruptions in cosmic development. Mountain ranges built by the tectonic stresses triggered by impact-induced seismic activity will undergo complete erosion and isostatic readjustment over tens of millions of years. Their elevated topography gradually reduced to sea level through the patient work of weathering and mass-wasting processes that operate with the persistence of natural law. The mountains that rose in response to crustal disruption will eventually contribute their mass to sedimentary basins and oceanic trenches, their exotic trace element signatures dispersed through the global sediment budget. The irony deepens across astronomical time Earth itself. Along with all evidence of the impact event and indeed all evidence of life's 4 billion-year evolutionary experiment, will eventually be consumed by the Sun's expansion into a red giant star as stellar evolution proceeds through its predictable sequence of nuclear fuel exhaustion and envelope expansion. The exotic isotopes from another stellar system that briefly enriched Earth's chemistry will be vaporized along with all terrestrial matter when solar expansion engulfs the inner planets in approximately 5 billion years. Ice core records, those annual accumulation layers in polar ice sheets that preserve detailed atmospheric histories, will eventually disappear as glacial flow delivers the ice to ablation zones or as climate change eliminates the polar ice caps entirely, erasing the high-resolution atmospheric chemistry records that document the immediate aftermath of interstellar collision. The precise temporal records of atmospheric response to exotic material injection will be lost as the ice that preserves them undergoes phase changes that destroy the stratigraphic integrity of annual layers. Fossil preservation of organisms that survive the impact event will create paleontological records that encode information about biological responses to extraterrestrial chemistry, though the specific cause of evolutionary changes will become increasingly difficult to determine as the geological context of fossilization sites changes through continued tectonic activity. The fossil record will show clear evidence of evolutionary bottlenecks and adaptive radiation, but the role of exotic trace elements in driving these biological changes may remain cryptic to future paleobiologists. Magnetic reversals, those periodic changes in Earth's magnetic field polarity that occur every few 100,000 years on average, will gradually overprint the paleomagnetic records of impact-related magnetic field disturbances, making it increasingly difficult to reconstruct the geomagnetic effects of the collision event. The magnetic signatures locked into cooling igneous rocks will be reset by subsequent heating events or obscured by the superposition of multiple magnetic field episodes. Radioactive decay of unstable isotopes produced by cosmic ray bombardment during the comet's interstellar journey will gradually reduce the concentrations of these exotic nuclides in terrestrial materials, their half-lives determining how long these chemical fingerprints remain detectable above background levels. Some isotopes will disappear within thousands of years, while others may persist for millions of years as traces of extraterrestrial input, their decay products contributing to the normal inventory of stable isotopes in Earth's crust. Oceanic crust recycling through seafloor spreading and subduction will eventually carry the chemical signatures of oceanic impact into the mantle, where high temperatures and pressures may either preserve or obliterate the isotopic evidence of extraterrestrial material input. The recycling time for oceanic crust averages approximately 200 million years, ensuring that most evidence of oceanic impact effects will be subducted and potentially homogenized with mantle chemistry within geological reasonable timespans. Atmospheric evolution continues its slow progression toward higher oxygen concentrations and different greenhouse gas compositions as biological and geological processes respond to changed environmental conditions. Modifications that will gradually erase the atmospheric chemistry anomalies created by exotic material injection. The atmosphere's composition will eventually equilibrate to new steady-state conditions determined by post-impact biological productivity and geochemical cycles, obscuring the atmospheric signature of interstellar chemistry input. The Great Unconformity, that vast gap in the geological record representing hundreds of millions of years of erosion that removed entire mountain ranges and continental platforms, demonstrates geology's capacity to erase even the most dramatic surface features through the patient operation of weathering and mass-wasting processes. The impact event, however significant in its immediate effects, will eventually face similar erasure as geological time reduces even the most prominent surface features to subtle chemical anomalies in sedimentary sequences. Galactic rotation will carry our solar system through different regions of the Milky Way galaxy over hundreds of millions of years, exposing Earth to varying cosmic ray fluxes and potentially different populations of interstellar objects as stellar density and composition change with galactic location. The specific combination of interstellar chemistry that characterized this impact event may never be repeated as our solar system's galactic neighborhood evolves through stellar birth and death cycles. Impact crater degradation follows predictable mathematical relationships that correlate crater preservation with target material properties, climate conditions, and tectonic activity rates, allowing geologists to estimate how long surface evidence of the collision will remain recognizable. The largest craters may preserve their circular geometry for tens of millions of years, but eventually even these will be reduced to subtle gravity anomalies and circular patterns in regional geology that require sophisticated analysis to detect. Only took deep time, 4.5 billion years, to transform Earth from a molten ball of rock and metal into a complex system capable of supporting life. And now the same temporal vastness that enabled this planetary evolution begins its patient work of incorporating the brief violence of interstellar collision into the ongoing story of cosmic evolution, ensuring that this moment of contact between stellar systems will eventually fade into the background noise of geological process, preserved only as subtle chemical anomalies in rocks that will themselves eventually be recycled through the slow but inexorable mechanisms that govern planetary evolution across the vast scales of astronomical time. The silence settles now across geological time, where moments of cosmic violence fade into the patient rhythm of erosion and deposition, the slow breathing of a planet that has witnessed countless such encounters across its 4.5 billion year journey around the Sun. In the deep ocean basins, sediments accumulate grain by grain, each microscopic particle carrying trace amounts of exotic chemistry that will remain embedded in Earth's rock record long after the last mountain built by impact-induced tectonics has been worn down to sea level by the quiet persistence of wind and water. The isotopic signatures slowly disperse through biogeochemical cycles, exotic elements from another stellar system gradually mixing with terrestrial chemistry until their alien origin becomes detectable only through the most sophisticated analytical techniques. Carbon atoms synthesized in the nuclear furnace of a distant star now participate in the photosynthesis of Earth's plants, their unusual neutron-to-proton ratios contributing infinitesimally to the global carbon cycle that has operated for billions of years. The boundary between terrestrial and extraterrestrial chemistry dissolves into statistical noise as deep time homogenizes all matter through the patient stirring of atmospheric circulation and oceanic currents, rock layers continue their accumulation above the thin chemical horizon that marks this moment. Limestone and sandstone and shale, building their testimony to Earth's ongoing evolution, one microscopic layer at a time. The violent energy that reshaped continents and triggered mass extinction becomes merely another entry in the stratigraphic column, no more or less significant than the countless other brief episodes of disruption that punctuate the geological record. Deep time renders all events equal in their temporal insignificance, reducing cosmic catastrophes to millimetre-thick boundaries between otherwise unremarkable sedimentary sequences. The last traces of atmospheric disturbance fade into the background variability of natural weather patterns as Earth's climate system slowly returns to equilibrium states determined by solar heating, oceanic circulation, and the greenhouse effects of water vapour and carbon dioxide. The exotic chemistry that briefly altered atmospheric composition becomes diluted beyond detection, dispersed through precipitation and atmospheric mixing, until it joins the vast inventory of trace elements that have accumulated from billions of years of meteorite infall and cosmic dust accretion, somewhere in the deep ocean trenches where tectonic plates descend into the mantle. Fragments of oceanic crust begin their journey into Earth's interior, carrying with them the chemical signatures of interstellar collision that will be recycled through magma generation and volcanic outgassing across hundreds of millions of years. The exotic isotopes become part of the planet's internal chemistry, their stellar origin lost to the homogenizing effects of high temperature and pressure that characterize geological processes in Earth's deep interior. The quiet mathematics of orbital mechanics continue to govern planetary motion with the same precision that brought the interstellar visitor to its moment of collision. Earth, maintaining its elliptical path around the Sun while the debris of impact disperses along ballistic trajectories that will eventually carry some fragments beyond the solar system entirely. The gravitational equations that orchestrated cosmic catastrophe now oversee the peaceful dispersal of evidence, spreading the chemical products of stellar nucleosynthesis across interplanetary space with the same mathematical inevitability that governed their arrival. In the fossil record, the biological responses to environmental disruption become preserved as evolutionary adaptations whose specific causes fade into paleontological speculation. Adaptive radiations and extinction events that mark the boundaries between geological epochs, but whose triggering mechanisms remain forever cryptic to future investigators. Life's resilience transforms catastrophe into opportunity, using environmental pressure as the driving force for evolutionary innovation that creates new species complexes adapted to post-impact conditions. The cosmic perspective settles over all terrestrial concerns as deep time asserts its dominance over immediate events, reducing the violence of interstellar collision to merely another moment in the vast story of planetary evolution that connects Earth's molten birth to its eventual consumption by an expanding sun. The same temporal framework that enabled the emergence of life from primordial chemistry now provides context for understanding how even the most dramatic events become absorbed into the ongoing narrative of cosmic evolution. Sleep now, in the knowledge that all things pass into the patient embrace of geological time, where the most violent cosmic encounters become merely brief interruptions in the slow but persistent processes that shape worlds across the vast scales of astronomical duration. The silence deepens into the eternal quiet of deep space, where matter drifts between star systems with the peace of infinite patience, waiting for the next moment when gravity will orchestrate another brief encounter between worlds separated by light years and geological ages, another instant of contact in the vast darkness where time itself becomes the only constant in the endless dance of cosmic evolution.